When people imagine the edge of the universe, they usually picture a border, a place where space stops. Maybe a wall, maybe a drop-off, maybe something you could point to if your telescope were powerful enough. That image feels natural because almost everything we deal with in daily life has an edge somewhere. The problem is that the universe does not behave like everyday objects. Modern cosmology says there is no known place where space simply ends. No outer shell, no final boundary. And yet, there is a very real sense in which our universe has limits, hard limits, on what we can see, measure, or ever interact with. These limits are not set by technology, they are set by physics itself. When astronomers talk about the edge of the universe, they are not talking about the end of space. They are talking about the edge of what is observable, the farthest light that can reach us, the oldest signals that still exist, the regions that are already slipping beyond any possible contact, even in principle. And this is where things get strange. The edge is not a place you could travel to. It moves. It depends on time. Some parts of the universe that exist right now are already unreachable forever. Others were once visible, but no longer are. The deepest boundary we can observe is not made of matter at all, but of ancient radiation left over from when the universe was less than 1 million years old. To understand why the universe's edge works this way, we have to rethink what distance, motion, and boundaries really mean on cosmic scales. When scientists use the phrase the edge of the universe, they are not describing a physical border in space. There is no confirmed location where space stops, thins out, or transitions into something else. The phrase survives mostly because it is convenient shorthand for something much more precise and much less intuitive: the limits of what can be observed from Earth, given the finite age of the universe and the finite speed at which information travels. The most important distinction to make at the beginning is between the universe itself and the observable universe. The universe, in the broadest sense, includes everything that exists: all space, all matter, all energy, and all physical laws. The observable universe is only the portion of that total universe from which light or other signals have had time to reach us since the beginning of cosmic expansion. These two are not assumed to be the same size. In fact, most cosmological models allow, and in many cases favor, the universe being vastly larger than what we can observe, possibly infinite. The observable universe is defined by a simple but strict rule. If light from a region of space has not had enough time to reach Earth since the universe became transparent, then that region is unobservable by any telescope, no matter how powerful. This limit is not about distance alone. It is about time. The universe has a finite age, currently measured at about 13.8 billion years. Light travels at a finite speed. Those two facts together impose a horizon on observation. Because of this, the observable universe has a measurable size. In today's terms, the radius of the observable universe is about 46 billion light-years. This number often confuses people because it is much larger than 13.8 billion. The reason is that space itself has been expanding while light was traveling. Light that began its journey when the universe was much smaller has been stretched along with the expansion of space, increasing the present-day distance between us and its point of origin. This already reveals something unintuitive about the edge. It is not defined by where things are now, but by where they were when their light was emitted. When we look at distant galaxies, we are not seeing them as they exist today. We are seeing snapshots of the past. The farther away an object is, the further back in time we are looking. At extreme distances, this effect dominates everything else. The edge of the observable universe is therefore not a wall in space, but a surface in time. It represents the earliest moments from which information can still reach us. This surface is sometimes described as a sphere surrounding the observer, but that description can be misleading. Every observer anywhere in the universe has their own observable universe, centered on themselves. There is nothing special about Earth in this respect. An observer in a distant galaxy would see a different set of galaxies within their observable universe, with Earth possibly near their own edge. This removes another common misconception, that the edge is a fixed place in space shared by all observers. It is not. Observability depends on where you are and when you are observing. The universe does not have a single universal observational boundary that everyone agrees on. Each location has its own horizon. Another key point is that the observable universe does not include everything that exists even within its own boundary at all times. Because the universe is expanding, the observable region changes. Some regions that were observable in the past are no longer observable today. Their light reached us once, but future light emitted from those regions will never reach us. This means that observability is not just limited, it can also be lost. This brings up the distinction between observational limits and physical boundaries. A physical boundary would imply that something fundamental changes at that location. A breakdown of physical laws, a transition to another medium, or the literal end of space. An observational limit, by contrast, says nothing about what exists beyond it. It only describes what we can, in principle, receive information from. When astronomers say that something is beyond the edge of the universe, they are using informal language. What they mean is that the object lies beyond our observational horizon. It still exists. It still follows the same physical laws as far as we can tell. It is simply causally disconnected from us, meaning that no signal from it can reach us now or in the future. This causal disconnection is essential. In physics, causality is tied to the ability of events to influence one another. If two regions of space cannot exchange signals, then events in one region cannot cause effects in the other. From a practical standpoint, this makes the regions independent. The edge of the observable universe is therefore also a causal boundary. However, it is not a boundary that you could detect locally. There is no experiment you could perform near the edge that would tell you that you are at the edge. Space does not behave differently there. Physical laws do not change. Matter does not thin out or behave strangely simply because it is near our observational limit. The edge is something we define from our perspective, not something that exists as a physical feature in space. Another subtle but important distinction is between distance limits and information limits. Even within the observable universe, there are objects whose current states we will never know. We can observe their past light, but we cannot observe what they are like now. The expansion of space means that the present-day universe is larger than the region from which present-day information can reach us. So even inside the observable universe, our knowledge is time-delayed and incomplete. This is why the phrase edge of the universe can be misleading if taken literally. It suggests a spatial termination when in reality the limit is temporal and informational. The universe does not present us with a final object or boundary at the edge. It presents us with older and older versions of the universe itself. As we look farther out, we see galaxies in earlier stages of development. Stars are younger. Structures are less evolved. Eventually, galaxies disappear entirely, replaced by a diffuse glow. This glow does not mark the end of space. It marks the last time the universe was transparent enough for light to travel freely. It is also worth noting that nothing special happens at the distance corresponding to the observable edge today. There is no shell of matter, no sudden cut-off in density. The edge is defined entirely by our observational constraints, not by any dramatic physical transition in space itself. This perspective helps clarify why questions like what is beyond the edge of the universe are scientifically meaningful but observationally unanswerable. Cosmology can propose models of what lies beyond our observable region, based on physical laws that appear uniform within it. But no observation can directly confirm those models because the information cannot reach us. So when discussing the edge of the universe, precision matters. We are not talking about the universe ending. We are talking about our view ending. The universe may extend far beyond that view, possibly without limit. The edge, in this context, is a boundary of knowledge imposed by the combination of cosmic age, light speed, and expansion. Everything we know about the universe beyond our immediate surroundings comes to us through signals, mostly light, sometimes other forms of radiation, and more recently, things like neutrinos and gravitational waves. But no matter the messenger, there is a hard rule they all obey. They travel at a finite speed. That single fact is one of the most important constraints in cosmology, and it is central to why the universe has observable limits at all. The speed of light in a vacuum is about 300,000 kilometers per second. In everyday terms, that feels unimaginably fast. Light can circle Earth more than 7 times in a single second. From the Moon, it takes just over a second to reach us. From the Sun, about 8 minutes. These numbers make it tempting to think of light as effectively instantaneous on large scales. On cosmic scales, it is not. The universe is not infinitely old. It has a finite age measured through multiple independent methods and currently estimated at about 13.8 billion years. That number sets a maximum time window for any signal to reach us. Even if light had been traveling toward Earth since the very beginning, it could not have been traveling for longer than the age of the universe itself. This immediately creates a limit. There are regions of space so distant that their light simply has not had enough time to arrive yet. Those regions are not hidden by dust, darkness, or lack of technology. They are hidden by time. This is where the concept of look-back time becomes essential. When astronomers observe a distant object, they are not seeing it as it is now. They are seeing it as it was when the light left it. If a galaxy is 1 billion light-years away, the light we observe today began its journey 1 billion years ago. That galaxy may look completely different now, but we cannot know that directly. As distance increases, look-back time increases with it. At sufficiently large distances, look-back time becomes comparable to the age of the universe. At that point, we are no longer observing galaxies as they formed billions of years ago. We are observing the universe itself in an early state. This relationship between distance and time is not optional. It is built into the structure of space-time. Every observation of the distant universe is also an observation of the past. However, even this picture is still too simple because it assumes that space itself is static while light travels through it. In reality, space is expanding. This complicates how distance and time relate, but it does not remove the fundamental role of light speed. It reinforces it. When light travels through expanding space, the distance between its starting point and its destination can increase while the light is in transit. This means that light can take much longer to reach us than a simple distance divided by speed calculation would suggest. It also means that the present-day distance to the source can be far larger than the distance implied by the light's travel time. This is why the observable universe has a radius much larger than 13.8 billion light-years. Light that has been traveling for 13.8 billion years can now be coming from regions that are tens of billions of light-years away in present-day distance. The finite speed of light sets the time limit, but expansion stretches the spatial scale. Despite this complexity, the core principle remains unchanged. Information cannot propagate faster than light. No matter how space expands, no signal from a region can reach us unless there has been enough time for that signal to travel. This has profound consequences for what can ever be observed. There are parts of the universe that exist right now whose light will never reach Earth, not because the universe will end, but because the expansion of space will always outrun the light trying to cross it. These regions are not just currently unobservable, they are permanently inaccessible. The finite speed of light therefore defines not just a current boundary, but a fundamental limit on causal contact. Causality, in physics, is about influence. If one event cannot influence another because no signal can travel between them, then those events are causally disconnected. Light speed is the ultimate governor of that connectivity. Another way to see this is to imagine freezing the universe's expansion for a moment. Even then, there would still be a maximum distance from which light could have reached us since the beginning. That distance defines a horizon. Expansion modifies the details, but the existence of a horizon comes directly from light's finite speed combined with finite time. This also explains why faster telescopes or better detectors cannot push us beyond certain limits. Technology can help us detect fainter signals or resolve finer details, but it cannot retrieve information that has not arrived. There is no way to see light that has not yet reached us, just as there is no way to hear a sound before the sound waves arrive. This is a different kind of limitation than most scientific limits. It is not about insufficient resolution or sensitivity. It is about the structure of space-time itself. Even a perfect detector cannot bypass the speed of light. The finite speed of light also means that the universe does not have a single universal now. Different regions are observed at different times in their histories. When we look across the sky, we are looking across a patchwork of cosmic times. Nearby objects are seen almost as they are now. Distant objects are seen as they were billions of years ago. This creates a universe where simultaneity breaks down on large scales. There is no way to observe the entire universe at one cosmic moment. Our picture is always a layered one built from signals that left their sources at different times. At extreme distances, this layering becomes dominant. Eventually, we reach a point where there are no longer any stars or galaxies to observe, not because they do not exist, but because the universe had not yet formed them at the time the light we are receiving was emitted. This again highlights that the edge we encounter is not spatial in the usual sense. It is temporal. We are running out of earlier moments to observe, not running into a wall in space. It is also important to emphasize that nothing special happens to light itself at the observable limit. Light does not slow down, stop, or fade out because it is approaching some cosmic boundary. The limit exists because there is only so much time available for light to travel before we reach the earliest eras of the universe. In summary, the finite speed of light transforms the universe into a place where distance is inseparable from time. Every faraway object is also a historical record. And because the universe has only existed for a finite duration, there is a hard cap on how much of that record we can ever access. In cosmology, the word horizon does not mean a physical edge or boundary in space. It refers to a limit on what can be observed or influenced, set by the behavior of space-time itself. Just as the horizon on Earth marks the farthest distance you can see from a given location, cosmic horizons mark limits on what information can reach an observer. These horizons arise naturally once you accept three facts at the same time. The universe has a finite age, space is expanding, and signals travel at a finite speed. There is more than one type of cosmic horizon, and each one captures a different aspect of what is observable or causally connected. The two most important are the particle horizon and the event horizon. They are often confused with each other, but they describe fundamentally different limits. The particle horizon defines the maximum distance from which light could have reached an observer since the beginning of the universe. It answers a backward-looking question. How far away could something be, such that its light has had enough time to arrive here by now? This horizon sets the size of the observable universe at a given moment in cosmic time. To understand the particle horizon, imagine the universe at its earliest moments. At the start of cosmic expansion, everything was extremely hot and dense. As time passed, light began to travel outward from every region in space. But because time itself had only just begun, light could not instantly fill the universe. At any later moment, there would always be regions that were simply too far away for their light to have arrived yet. The particle horizon grows with time. As the universe ages, light has more time to travel and the observable region expands. This is why the observable universe today is vastly larger than it was billions of years ago. The longer the universe exists, the larger the volume from which light has had time to reach us. However, this growth is not linear or simple because space itself is expanding while light travels through it. Early in the universe's history, expansion was extremely rapid. Later, it slowed, and more recently, it has accelerated again. These changes affect how quickly the particle horizon grows in terms of present-day distance. Even so, the core idea remains straightforward. The particle horizon marks the farthest distance from which particles or light signals could have arrived since the beginning. Anything beyond that horizon has not yet had time to influence us in any way. The particle horizon is not fixed in space. It is defined relative to the observer and changes with time. An observer today has a much larger particle horizon than an observer living billions of years ago would have had. Likewise, observers in different locations each have their own particle horizon centered on themselves. This also means the particle horizon is not symmetric between observers. Two observers separated by a large distance will not agree on which regions lie within their respective observable universes. Each sees a different cosmic neighborhood, bounded by their own horizon. The event horizon, by contrast, answers a forward-looking question. Instead of asking how far light could have come from in the past, it asks how far light emitted now can ever travel in the future. It defines the maximum distance to which signals sent today can ever reach, even if the universe continues forever. This is a subtler concept because it depends on the future behavior of cosmic expansion. If the universe were not expanding, or if its expansion was slowing enough, there might be no event horizon at all. Signals emitted today could eventually reach arbitrarily distant regions, given enough time. But our universe does not behave that way. Observations show that the expansion of the universe is accelerating, driven by something commonly referred to as dark energy. Because of this acceleration, there are regions of space that are already receding from us so rapidly that light emitted from here today will never reach them. The event horizon marks the boundary between regions that can, in principle, ever be influenced by us and regions that cannot. Anything currently beyond the event horizon is causally disconnected from our future. No matter how long the universe lasts, no signal we send now will ever cross that boundary. This is not because the signal fails or fades, but because the expansion of space continually increases the distance the signal must traverse. Beyond a certain point, the expansion always outpaces the signal's progress. The gap never closes. It is important to stress that the event horizon is not the same as the particle horizon. There are regions of the universe whose light has reached us in the past, but that lie beyond our event horizon. We can see their ancient light, but we can never influence their future or receive any new information from them beyond what has already arrived. This distinction highlights a strange feature of cosmic horizons. Visibility and influence are not the same thing. Seeing something does not mean it is causally connected to us now or in the future. Both horizons depend on the expansion history of the universe, but in different ways. The particle horizon depends on how the universe expanded in the past, from the beginning until now. The event horizon depends on how the universe will expand in the future, from now onward. Because expansion has changed over time, the behavior of these horizons has also changed. In the early universe, when expansion was extremely rapid, regions were quickly pushed out of causal contact. Later, when expansion slowed, horizons grew more quickly in terms of co-moving distance, allowing more regions to come into causal contact. In the current era of accelerated expansion, event horizons have become a dominant feature. Another crucial point is that cosmic horizons are not physical barriers. There is no wall or boundary at the horizon. If you were somehow located at the distance corresponding to our event horizon, nothing about your local environment would tell you that you were at a special place. Physics would behave the same way it does elsewhere. Horizons are defined globally, not locally. They are properties of space-time as a whole, not features embedded within it. You cannot detect a horizon by local experiments alone. This is why the term cosmic horizon can be misleading if interpreted too literally. It does not describe a thing in space. It describes a relationship between space-time, motion, and causality. Another important aspect of horizons is that they are observer-dependent. Each observer has their own particle horizon and event horizon centered on their own position in space. There is no single universal horizon shared by all observers. This observer dependence is a direct consequence of the finite speed of light and the expansion of space. Because information takes time to travel, and because distances evolve, what is observable from one location is not identical to what is observable from another. Horizons also introduce limits on knowledge. There are facts about the universe that are, in principle, unknowable to a given observer, because the information needed to determine them lies beyond their horizons. This is not a practical limitation. It is a fundamental one. For example, we cannot know the present-day state of regions that lie beyond our event horizon. We can infer properties based on physical laws and early conditions, but we cannot directly observe or test those inferences. No future improvement in technology can change that. The fact that horizons evolve over time adds another layer of complexity. The particle horizon grows as the universe ages, but the event horizon can shrink or grow depending on how expansion behaves. In an accelerating universe, the event horizon encloses a finite region that effectively isolates observers from most of the cosmos. This means the universe is not just large, it is dynamically partitioned into regions that lose causal contact over time. What is accessible now may not remain accessible indefinitely. It is also worth noting that horizons are not sharp in a physical sense. There is no sudden cutoff in density, radiation, or structure at a horizon. The transition is conceptual, not material. Objects do not behave differently simply because they are near a horizon distance. All of this reinforces a key idea. Cosmic horizons are limits defined by time, expansion, and light speed, not by matter distribution or physical walls. They are mathematical features of space-time that describe what can be seen and what can be influenced. Understanding the difference between the particle horizon and the event horizon is essential for any serious discussion of the universe's limits. One tells us how much of the universe we can see now. The other tells us how much of it we can ever affect or learn more about in the future. One of the most persistent misunderstandings in cosmology is the idea that galaxies are flying through space away from us, like debris from an explosion. That picture feels intuitive, but it is wrong in a crucial way. On the larger scales, galaxies are not primarily moving through space. Space itself is expanding, and galaxies are being carried along with that expansion. This distinction matters because it changes how distance, motion, and speed work in the universe. It also explains why some distant galaxies appear to recede from us faster than light without violating any laws of physics. To see why, start with what astronomers actually observe. When they look at distant galaxies, they measure a systematic redshift in the light coming from them. The farther away a galaxy is, the more its light is shifted toward longer wavelengths. This relationship is remarkably consistent and is known as the Hubble-Lemaitre relation. At first glance, it looks exactly like a Doppler effect, galaxies moving away, stretching the light waves behind them. But this interpretation only works locally. On small scales, galaxies do have motions through space. Nearby galaxies can approach or recede due to gravitational interactions. The Andromeda Galaxy, for example, is moving toward the Milky Way. That motion is real and happens within space. On large scales, however, a different effect dominates. The redshift of distant galaxies is not mainly due to their motion through space, but due to the expansion of space itself. As light travels across the universe, the space it moves through stretches, and that stretching increases the wavelength of the light. This is called cosmological redshift, and it is fundamentally different from ordinary motion-based redshift. The galaxy does not need to be moving away in the everyday sense for its light to be redshifted. Even a galaxy at rest relative to the expanding space around it will show redshift if the space between it and the observer expands while the light is in transit. To make this concrete, imagine space as a flexible grid with galaxies embedded in it. The galaxies stay in roughly the same positions relative to the grid, but the grid itself stretches over time. As the grid stretches, the distance between galaxies increases even though the galaxies are not actively moving through the grid. This picture immediately resolves a major puzzle: why very distant galaxies appear to recede faster than light. In special relativity, nothing can move through space faster than light. But general relativity, which governs cosmology, allows space itself to expand at any rate. When astronomers say a galaxy has a recession speed greater than light, they are describing how quickly the distance between us and that galaxy is increasing due to expansion, not how fast the galaxy is traveling locally through space. This distinction between motion through space and expansion of space is not semantic. It is built into the mathematical description of the universe. That description comes from general relativity, which does not treat space as a static stage on which events happen. Instead, space and time together form space-time, a dynamic entity that can stretch, curve, and evolve. In cosmology, the large-scale behavior of space-time is described by a metric, a mathematical object that defines how distances are measured. The standard cosmological metric assumes that the universe is, on large scales, homogeneous and isotropic. That means it looks roughly the same everywhere and in every direction when averaged over large distances. Under those assumptions, the metric includes a scale factor that changes with time. This scale factor is what encodes the expansion of space. When the scale factor increases, all large-scale distances increase with it. Galaxies that are not gravitationally bound to each other move farther apart because the underlying metric that defines distance is changing. This process is called metric expansion. Metric expansion does not pull apart everything indiscriminately. Forces still matter. On small scales, gravity, electromagnetism, and nuclear forces easily overpower the effect of cosmic expansion. Atoms do not expand. People do not expand. Solar systems do not expand. Even galaxies and galaxy clusters, once gravitationally bound, largely resist expansion internally. This is why expansion is not something you can measure in a laboratory or even within a galaxy. It only becomes noticeable on scales where gravitational binding is weak compared to the overall stretching of spacetime. The transition between bound and expanding systems is gradual, not sharp. Small groups of galaxies can remain bound, while larger separations follow the expansion. This is why the local group of galaxies, including the Milky Way and Andromeda, does not participate in the general expansion, even though distant galaxies do. Understanding expansion as a property of space itself also clarifies why the universe does not have a central point from which everything is expanding. In an explosion, debris flies outward from a specific location. In cosmic expansion, every location sees other distant locations moving away on average. No matter where you are, the universe appears to expand around you. This is not an illusion. It is a direct consequence of uniform expansion. The expansion does not have a center within space, because it is not expansion into space. It is expansion of space. This also explains why the observable universe looks similar in every direction. There is no preferred direction or edge built into the expansion. The large-scale structure appears statistically similar no matter where you look, because the metric expansion treats all directions equally. Now consider what this means for distant galaxies. The farther away a galaxy is, the more space there is between it and us, and therefore the more expansion affects the light travelling from it. Light emitted billions of years ago has had its wavelength stretched by the cumulative expansion of space over its entire journey. This stretching does not just shift colours, it also reduces the energy of the light. Each photon loses energy as its wavelength increases. This is why very distant objects are faint, not only because of distance, but also because of redshift. At extreme distances, the expansion becomes so significant that entire classes of objects become effectively unobservable. Their light is stretched to such long wavelengths that it blends into background radiation or becomes undetectable by practical instruments. This is not because the objects vanish, but because the expanding metric alters how their signals arrive. Expansion also affects how distances are defined and compared. In everyday life, distance is straightforward. In cosmology, there are multiple distance measures, each useful for different purposes. There is proper distance, co-moving distance, luminosity distance, and angular diameter distance. These are not interchangeable, and they behave differently as the universe expands. Co-moving distance, in particular, is useful for describing expansion. It factors out the expansion by using coordinates that expand with space. Galaxies at rest in co-moving coordinates remain at fixed positions even as the universe grows. Proper distance, by contrast, increases as the scale factor increases. This distinction matters when discussing horizons and limits. A galaxy can have a fixed co-moving distance and still move beyond an event horizon in terms of proper distance. Expansion changes the relationship between coordinate position and physical separation over time. One of the more counterintuitive consequences of metric expansion is that light can move toward us locally while the overall distance to its source increases. Early in the universe's history, light emitted by some galaxies initially moved closer to us in co-moving terms, but the rapid expansion caused the proper distance to increase faster than the light could close the gap. Only later, as expansion slowed, did the light make net progress toward us. This behavior would be impossible in a non-expanding space. It arises specifically because the metric defining distance is evolving while the light travels. Metric expansion also means that there is no global notion of velocity that applies universally across the universe. The idea of how fast a distant galaxy is moving away depends on how you define distance and time, and those definitions depend on the metric. This is why recession speeds can exceed the speed of light without contradiction. They are not local velocities measured in a single inertial frame. For distant galaxies, expansion has another crucial consequence: loss of causal contact. As the universe expands, some galaxies cross our event horizon. Once that happens, no signal emitted by them after that moment can ever reach us. They are not destroyed, they simply become causally disconnected. From our perspective, those galaxies gradually fade. Their light becomes more redshifted and dimmer over time. Eventually, they disappear from view entirely. This disappearance is not due to motion through space, but to the stretching of space itself. This process is ongoing. Even galaxies we can observe today may not remain observable forever. Expansion is not just something that happened in the past. It continues to shape what parts of the universe are accessible now and in the future. The expansion of space also influences how structures form and evolve. In the early universe, expansion competed with gravity. Regions with slightly higher density could collapse to form stars and galaxies, while expansion pulled matter apart elsewhere. The balance between expansion and gravitational attraction determined which structures could form and which could not. As expansion accelerates, this balance shifts. Gravity has less time to pull matter together across large distances. Structure formation slows and eventually freezes on the larger scales. This is another consequence of metric expansion, not of galaxies actively fleeing from one another. It is important to emphasize that expansion does not imply the universe is expanding into something else. There is no surrounding space into which our universe grows. The metric expansion describes how distances within the universe change relative to each other, not how the universe interacts with an external environment. This is often difficult to accept because human intuition is built around motion through pre-existing space. General relativity replaces that intuition with a model in which space itself is part of the system being described. When discussing the universe's edge, this matters because expansion determines what is reachable and what is not. The edge is not fixed in space. It evolves as the scale factor evolves. Regions that are within reach at one time may fall out of reach at another, not because they move faster, but because the underlying geometry changes. All of these consequences follow from the same core idea. Space is dynamic. It expands according to the laws of general relativity, and that expansion governs large-scale cosmic behavior. Without metric expansion, the universe would look radically different. There would be no cosmological redshift as observed, no consistent relationship between distance and redshift, no natural explanation for superluminal recession, and no horizons of the type we observe. The expansion of space itself is therefore not a secondary detail. It is the framework within which all large-scale cosmic limits are defined. One of the most unsettling facts about the universe is that some galaxies we can see right now are already beyond our ability to ever interact with again. Not in the distant future. Not after some dramatic cosmic event. Already. This is not a matter of technological limitation. It is not about propulsion, communication systems, or engineering challenges. It is a consequence of how space expands and how causality works in an expanding universe. To understand why some galaxies are unreachable, we have to be precise about what reachable means in physics. Reachability is not about whether we could travel there with a sufficiently powerful spaceship. It is about whether any signal or influence moving at or below the speed of light can ever cross the distance between us and that galaxy. If no signal can ever make that journey, then the galaxy is causally disconnected from us. From the standpoint of physics, it might as well belong to a separate universe. The key idea is that in an expanding universe, distance is not a static quantity. The space between objects changes over time. For nearby galaxies, the expansion is slow enough that signals can still cross the gap. For very distant galaxies, the expansion is so rapid that the gap grows faster than light can close it. This leads to a counterintuitive but well-established result. There are galaxies whose light we can see today, but from which no new light emitted today will ever reach us. To see how this works, consider what happens when a distant galaxy emits a photon toward Earth. The photon always moves locally at the speed of light. That never changes. But while the photon is traveling, the space it moves through is expanding. If the rate of expansion is high enough, the distance between the photon and its destination can increase even as the photon moves forward. In nearby regions of space, expansion is slow compared to the photon's progress. The photon steadily reduces the distance to Earth and eventually arrives. In very distant regions, expansion can dominate. The photon still moves toward Earth locally, but the expanding space stretches the path faster than the photon can traverse it. This is not a paradox, it is a direct consequence of general relativity, where motion through space and the evolution of space itself are distinct concepts. The point at which expansion overtakes light defines a boundary in terms of causal influence. Galaxies beyond that boundary are receding from us so rapidly due to expansion that signals emitted now can never reach us. This boundary is not the same as the particle horizon, which marks how far light from the past has already reached us. Instead, it is tied to the event horizon, which marks the limit of future influence. A galaxy can be within our particle horizon, meaning we can see its ancient light, while simultaneously being beyond our event horizon, meaning we can never receive any new information from it. This is why reachability and visibility are not the same thing. To make this more concrete, imagine a galaxy whose light began traveling toward us billions of years ago, when the universe was smaller and expansion was slower. That light had a chance to make progress. Over time, it eventually reached Earth, and we detect it with our telescopes today. But since then, the universe has continued to expand. In fact, expansion has accelerated. The galaxy's present-day distance from us may now be increasing so rapidly that any light it emits today is effectively carried away by the expanding space. That light will never catch up. From our perspective, the galaxy exists. We can see it, but it is already beyond causal reach. This also means that if we were to send a signal toward that galaxy today, the same logic applies. The signal would never arrive. The space between us and the galaxy would continue to expand, maintaining or increasing the separation faster than the signal could reduce it. This result does not depend on the nature of the signal. It applies to light, radio waves, neutrinos, gravitational waves, or any other form of information transfer allowed by physics. If it travels at or below the speed of light, it is subject to the same limit. Another important detail is that this loss of reachability happens gradually, not suddenly. There is no dramatic moment when a galaxy crosses a visible line and vanishes instantly. Instead, the process unfolds over cosmic time, and as a galaxy approaches the event horizon, its light becomes increasingly redshifted. Each successive wave is stretched more than the last. The galaxy appears dimmer and redder. Its apparent rate of evolution slows. From our point of view, processes in that galaxy seem to take longer and longer to unfold. Eventually, the galaxy fades beyond detectability. Not because it ceases to exist, but because its light is stretched to wavelengths so long and energies so low that it blends into the background or becomes undetectable in practice. This fading is permanent. Once a galaxy passes beyond the event horizon, no new information from it can ever reach us. The last photons we receive carry the final snapshot we will ever have of that region of the universe. This has a striking implication. The observable universe is not just limited in space, but also in time. Our view of some regions freezes at a certain moment in their history. Whatever happens there afterward is forever hidden from us. It is also important to emphasize that galaxies do not need to be extraordinarily distant to become unreachable. The precise distance depends on the expansion rate of the universe and how it changes over time. In a universe with accelerating expansion, the event horizon encloses a finite region. Galaxies beyond that region are already lost to us in terms of future contact, even if we can still see their ancient light today. This challenges another common intuition, that the universe is slowly revealing more of itself over time. While it is true that the particle horizon grows and we can see more of the early universe as time passes, the opposite is happening in terms of future connectivity. The set of regions we can ever interact with is shrinking. There is a subtle balance here. We can see more of the past, but we can influence less of the future. This distinction matters because it highlights the role of dark energy and accelerated expansion. In a universe without acceleration, distant regions might remain reachable, given enough time. Accelerated expansion changes that. It locks in causal disconnection. Another misconception is that unreachable galaxies are moving away from us because of some initial push or explosion. In reality, they are simply following the expansion of space. They are not trying to escape. There is no force flinging them outward. The metric that defines distance between us and them is evolving in a way that increases separation faster than signals can compensate. This also means that unreachable does not imply isolated in an absolute sense. Those galaxies may still interact with nearby galaxies. They may form clusters, stars, planets, and possibly life. They are only unreachable relative to us. From their own perspective, they have their own observable universe and their own event horizon. They may be able to see and interact with regions we can never observe. Causal disconnection is symmetric but observer-dependent. Another key point is that reachability is directional in time. A galaxy that is unreachable from us in the future was not necessarily unreachable in the past. There was a time when signals could cross the distance. That is why we can see its ancient light now. This reinforces the idea that cosmic limits are dynamic. They depend on when you ask the question, not just where things are located. The fact that some galaxies are already unreachable also has implications for any hypothetical future civilization. No matter how advanced, no civilization can expand indefinitely across the universe. There is a maximum region that can ever be accessed, set by the event horizon. This is not a pessimistic conclusion. It is a physical one. The universe does not permit unlimited causal reach. It also reframes the idea of cosmic exploration. Exploration is not about reaching everything that exists. It is about navigating a finite, shrinking domain of influence embedded in a much larger, possibly infinite universe. So another subtle implication is that the universe does not become more connected over time. On the larger scales, it becomes less connected. Regions drift into isolation as expansion accelerates. This is the opposite of what intuition might suggest if one imagines gravity eventually pulling everything together. On very large scales, expansion wins. Finally, it is worth stressing that none of this depends on speculative physics. The existence of unreachable galaxies follows directly from well-tested observations: cosmic expansion, its acceleration, and the finite speed of light. The mathematics involved is standard cosmology. The universe is not hiding these galaxies behind a curtain. It is separating from them in a way that makes future interaction impossible. They are not gone. They are simply no longer part of our causal world. There is a point in the observable universe beyond which no telescope, no detector, and no future technology can see using light. This boundary is not marked by darkness or emptiness. It is marked by radiation, faint, uniform, and ancient. This radiation is known as the cosmic microwave background, or CMB, and it represents one of the most important observational limits in cosmology. The cosmic microwave background is not just another distant object. It is a signal that comes from everywhere in the sky, in every direction, with almost the same intensity. It fills space uniformly. And crucially, it does not originate from stars or galaxies. It originates from the universe itself, at a specific early stage in its history. To understand why the CMB acts as a boundary, we have to go back to a time when the universe looked nothing like it does today. In the early universe, matter was extremely hot and dense. Temperatures were so high that atoms could not exist. Electrons and atomic nuclei were not bound together. Instead, they formed a hot, ionized plasma. In this state, light could not travel freely. Photons constantly collided with free electrons. Every attempt by light to move any significant distance was immediately interrupted by scattering. The universe during this phase was effectively opaque. Not dark, but opaque, filled with radiation that could not propagate freely over long distances. This situation persisted for hundreds of thousands of years after the beginning of cosmic expansion. During that entire time, the universe was glowing intensely, but no photon could travel far without being scattered. There was no clear line of sight across space. No direct information could propagate over large distances. As the universe expanded, it cooled. Expansion diluted energy and lowered temperatures. Eventually, the universe reached a point where it became cool enough for electrons and nuclei to combine into neutral atoms. This process is called recombination, though it is somewhat misnamed because it was the first time atoms formed, not a recombination in the usual sense. Once atoms formed, the universe changed dramatically. Neutral atoms do not scatter light nearly as efficiently as free electrons. Suddenly, photons were able to travel long distances without constant interruption. The universe transitioned from opaque to transparent. The moment when this happened marks a fundamental observational boundary. The photons released at that time have been traveling through space ever since. Over billions of years of expansion, their wavelengths have been stretched dramatically. What was once high-energy radiation is now observed as low-energy microwave radiation. That is the cosmic microwave background we detect today. When we observe the CMB, we are seeing the universe as it was at the moment it became transparent. We are not seeing beyond that moment using light because before that moment, light could not carry information freely. This is why the CMB acts as a wall of sorts. Not a wall in space, but a wall in time. It marks the earliest epoch from which electromagnetic radiation can reach us directly. Every direction we look, if we look far enough back, we eventually run into the CMB. Beyond it, there is no direct electromagnetic information available. The universe does not become empty beyond that point. It becomes hidden from view by its own early opacity. This boundary is often described as the surface of last scattering. That phrase captures the idea precisely. It is the surface from which the photons we now observe last scattered off matter before traveling freely through space. Calling it a surface can be misleading, though. It is not a physical shell or layer embedded in space. It is a spherical boundary centered on the observer, defined by look-back time. Every observer, anywhere in the universe, has their own surface of last scattering. From Earth, the CMB appears as a nearly uniform glow across the sky. Tiny variations in temperature and intensity exist, but the average temperature is almost the same in every direction. This uniformity was one of the earliest clues that the universe is homogeneous on large scales. The CMB's role as a boundary comes from the physics of light propagation, not from the absence of matter. Beyond the surface of last scattering, matter still existed. Radiation still existed. But photons were trapped in a dense plasma, unable to travel freely and carry information across large distances. This is a crucial distinction. The boundary is not caused by distance alone. It is caused by conditions in the early universe. Even if the universe were much smaller, the same limitation would apply. As long as matter was ionized and opaque to radiation, light could not serve as a messenger. The CMB marks the moment when that changed. This also means that the boundary is wavelength dependent. It applies to electromagnetic radiation. Light, radio waves, microwaves, all forms of electromagnetic radiation are subject to this limit. Now, other messengers are not necessarily subject to the same constraint. Neutrinos, for example, decoupled from matter much earlier than photons did. Gravitational waves may also carry information from earlier epochs. But when it comes to light, the CMB is the hard limit. This is why telescopes, no matter how powerful, cannot see earlier than the CMB using light. Increasing sensitivity does not help. There is simply no light from earlier times that has travelled freely to us. The CMB therefore defines the deepest electromagnetic view we can ever have of the universe. Another important aspect of the CMB boundary is that it does not correspond to a single moment everywhere in space. Recombination did not happen instantaneously. It occurred over a range of time as the universe cooled. As a result, the surface of last scattering has a finite thickness in time. The photons we observe today were released over a span of thousands of years, not at a single instant. This thickness introduces subtle effects in the observed properties of the CMB, but it does not change its role as a boundary. When we map the CMB, we are effectively looking at a spherical shell around us, corresponding to a time about 380,000 years after the beginning of cosmic expansion. That shell is incredibly distant in terms of present-day distance because of subsequent expansion, but its defining feature is temporal, not spatial. The CMB also represents the limit of direct observation of structure formation using light. Before recombination, matter fluctuations existed, but they were tightly coupled to radiation. After recombination, matter could collapse under gravity to form stars and galaxies. The tiny temperature variations seen in the CMB encode information about those early fluctuations. They are imprints of density differences that later grew into the large-scale structure of the universe. But they do not show stars, galaxies, or any familiar objects. They show the universe before such objects existed. This reinforces the idea that the CMB boundary is not the end of the universe's story. It is the beginning of a new observational regime. Beyond it lies a period that must be studied indirectly. Another reason the CMB is often described as an edge is that it appears isotropic. No matter where you look, you see it. There is no direction where you can see past it using light. It surrounds us completely. This can create the false impression that we are somehow at the center of the universe. In reality, the same would be true for any observer anywhere. Each observer sees their own CMB sphere centered on themselves. The CMB does not mark a special place in space. It marks a special time in cosmic history. It is also important to note that the CMB boundary is not static in co-moving coordinates. As time passes, the CMB photons continue to travel outward. The surface of last scattering recedes in co-moving distance. However, because it corresponds to a fixed epoch in time, it always represents the same moment in the universe's history. From our perspective, we will never see earlier electromagnetic information than what is encoded in the CMB. No amount of waiting changes that because earlier, photons never traveled freely. This makes the CMB a kind of observational ceiling for light-based cosmology. It sets a firm limit on what questions can be answered directly using electromagnetic signals. The existence of this boundary also explains why cosmology relies so heavily on theoretical modelling for the universe's earliest moments. For times earlier than recombination, we must infer conditions from their effects on later observables, such as the CMB's temperature fluctuations and polarization patterns. The boundary is therefore both a limit and a resource. While it blocks direct observation of earlier times, it preserves a pristine snapshot of the universe at a crucial moment. The CMB is not distorted by later structure formation. It comes to us almost unchanged aside from cosmic expansion. This makes it an exceptionally clean source of information about early conditions, but it does not remove the boundary itself. Another subtle point is that the CMB boundary is not aligned with the particle horizon exactly. The particle horizon marks the farthest distance light could have travelled since the beginning. The CMB marks the farthest distance light could have travelled freely since recombination. Before recombination, light existed, but it did not carry long-range information. So while the particle horizon includes earlier times in principle, the CMB marks the practical limit of electromagnetic observation. This distinction is important because it shows that not all horizons are defined the same way. Some are defined by causality and light speed. Others are defined by the physical state of matter and radiation. The CMB is an example of the latter. It is a boundary created by the interaction between light and matter. It also explains why the universe does not look infinitely old or chaotic when we look far away. Instead of seeing an endless sequence of older galaxies, we eventually see a smooth, nearly uniform glow. That glow is the universe itself, before structure formed. The cosmic microwave background is therefore not just background noise. It is the visible imprint of a transition from opacity to transparency. It is the earliest light we can ever observe. Beyond it, the universe continues, but light cannot tell us directly what it was like. The cosmic microwave background marks the earliest time from which light can reach us freely, but it does not mark the beginning of the universe, and it does not mark the beginning of matter, energy, or physical processes. It marks the end of a long period during which the universe was opaque to electromagnetic radiation. Before that boundary, the universe was very real, very active, and very different from anything we can observe directly with light. To understand what existed before the CMB wall, the first thing to discard is the idea of darkness. The early universe was not dark. It was overwhelmingly bright. Radiation dominated everything. The problem was not the absence of light, but the impossibility of light traveling freely. In the period before recombination, the universe was filled with a hot, dense plasma. This plasma consisted mainly of free electrons, protons, helium nuclei, and a vast number of photons. Temperatures were so high that electrons could not remain bound to nuclei. Any attempt to form a neutral atom was immediately undone by energetic photons. In this state, light and matter were tightly coupled. Photons constantly scattered off free electrons through a process called Thomson scattering. The mean free path of a photon, the average distance it could travel before being scattered, was extremely short. Instead of moving in straight lines across space, photons performed a kind of random walk, colliding endlessly with charged particles. Because of this, the universe was effectively opaque. Information carried by photons could not propagate over large distances. Any local disturbance in radiation or matter was quickly scrambled by interactions with the surrounding plasma. This opacity is what creates the CMB boundary. When the universe cooled enough for electrons to bind to nuclei and form neutral atoms, scattering dropped dramatically. Photons were suddenly released from this plasma and allowed to travel freely. Those photons are what we now observe as the CMB. Before that moment, light existed everywhere, but it could not act as a long-range messenger. The physical conditions before recombination were extreme by everyday standards, but they were governed by well-understood physics. The laws of electromagnetism, thermodynamics, and nuclear physics all applied. There is no indication that physical laws were different in this era, only that temperature and density pushed matter into regimes we no longer see naturally. The universe during this time was remarkably uniform on large scales. Density variations existed, but they were small. These variations are precisely what we later observe as tiny temperature fluctuations in the CMB. Before recombination, those fluctuations were present in the plasma itself. Because photons and matter were tightly coupled, radiation pressure played a major role in shaping these fluctuations. Gravity tried to pull matter into denser regions, while radiation pressure pushed back. The result was a pattern of oscillations in the plasma, often referred to as acoustic oscillations. These oscillations are not hypothetical. They left measurable imprints in the CMB. The peaks and troughs in the CMB's power spectrum correspond to sound waves that existed in the plasma before recombination. This means that when we study the CMB, we are indirectly studying conditions that existed before the CMB wall itself. However, even with this indirect access, there are strict limits on what light-based observation can reveal about earlier times. Before recombination, electromagnetic radiation cannot provide us with images, structures, or direct snapshots. It can only leave statistical imprints that survive the transition to transparency. This sharply limits the kind of information available. Going further back, conditions become even more extreme. As we move earlier in cosmic history, temperatures rise, densities increase, and matter transitions into states we cannot reproduce directly, except in limited experimental settings. Earlier still, the universe enters an era where atomic nuclei themselves cannot exist. Protons and neutrons collide with such high energies that they are constantly created and destroyed. Even earlier, protons and neutrons dissolve into their constituent quarks and gluons, forming a quark-gluon plasma. All of this happens long before the CMB boundary, but none of it is directly observable with light. Our knowledge of these eras comes from theoretical models tested against later evidence, such as element abundances and the detailed structure of the CMB. Another key feature of the pre-CMB universe is that it was expanding and cooling rapidly. Expansion was not a background detail. It drove the entire sequence of transitions. As space expanded, energy densities dropped, temperatures fell, and new forms of matter became stable. This expansion also means that the universe before recombination was much smaller in terms of proper distance. Regions that are now separated by vast distances were once extremely close together. This proximity explains why the early universe was so uniform, despite later expansion spreading matter across enormous scales. However, this uniformity also presents a puzzle. Regions on opposite sides of the CMB sky appear to have nearly the same temperature and properties, even though, under simple expansion, they should never have been in causal contact before recombination. This issue points to physics even earlier than the plasma era, but at this stage it is enough to note that the pre-CMB universe was already structured in ways that require explanation. The opacity of the early universe also means that it behaved very differently from the transparent universe we see today. There were no stars, no galaxies, no planets, and no complex structures. Matter had not yet fragmented into isolated objects. Everything was part of a continuous interacting medium. This makes the CMB boundary especially sharp conceptually. On one side of the boundary, the universe is transparent, structured and dominated by isolated objects emitting light. On the other side, the universe is opaque, smooth, and dominated by collective behavior. It is also important to emphasize that the CMB boundary is not associated with a physical barrier or sudden change in location. If you were present in the universe at a time just before recombination, you would not encounter a wall or a surface. You would simply be immersed in a dense, glowing plasma. The boundary exists only when we look backward in time from a much later epoch. Another subtle point is that while electromagnetic radiation cannot give us direct access to times before recombination, other messengers are not subject to the same limitation. Neutrinos decoupled from matter much earlier, when the universe was far hotter and denser. Gravitational waves may also carry information from very early times. However, detecting these signals is extraordinarily difficult, and they do not provide the same kind of spatial imaging that light does. They offer indirect glimpses, not visual maps. As a result, the pre-CMB universe is known primarily through inference. We infer its properties by asking what conditions must have existed to produce the universe we observe later. The success of this approach is measured by consistency, not direct observation. This makes the CMB wall a dividing line between two modes of knowledge. After recombination, we can observe the universe directly with light. Before recombination, we rely on theory constrained by later evidence. The existence of this limit does not mean the earlier universe is unknowable. It means it is knowable only in a different way. Precision measurements of the CMB, element abundances and large-scale structure all encode information about pre-CMB conditions. But none of this removes the fundamental fact. Light cannot show us the universe before it became transparent. The universe before the CMB wall was real, dynamic, and governed by physical laws we still use today. It was not hidden because it was distant. It was hidden because it was opaque. That opacity is what creates one of the clearest and most unavoidable boundaries in cosmology, a boundary not of space, but of observation. Long before the cosmic microwave background was released, long before atoms formed, and even before the hot plasma phase described earlier, the universe may have undergone a brief but extraordinary episode of expansion known as inflation. This idea was introduced to explain several otherwise puzzling features of the observable universe, and it radically changes how we think about the universe's size and extent. Inflation refers to a period during which space itself expanded at an extremely accelerated rate. This expansion was not just faster than the expansion we see today, it was exponentially faster. Distances between points in space increased by enormous factors in a tiny fraction of a second. It is important to be precise here. Inflation is not simply very fast expansion. It is a specific dynamical process in which the scale factor of the universe grows exponentially for a short time due to the behavior of a high-energy field permeating space. The details of that field are still under investigation, but the consequences of such expansion are well defined. One of the most immediate effects of inflation is that it dramatically increases the size of the universe. Regions that were once microscopically small were stretched to astrophysical and even cosmological scales. This stretching did not just affect distances, it affected the entire causal structure of the universe. Before inflation, the universe could have been extremely small, hot, and dense. During inflation, space expanded so rapidly that regions which were once in close causal contact were pushed far apart. After inflation ended, the universe continued expanding, but at a much slower rate, entering the hot, dense phase that eventually led to recombination and the CMB. This sequence has a critical implication. The observable universe today may represent only a tiny fraction of the total universe that inflation produced. To see why, consider what inflation does to horizons. During inflation, the expansion rate is so high that the particle horizon behaves very differently than in later eras. Regions that were initially within a single causal patch are stretched beyond each other's horizons. After inflation ends, those regions are no longer in causal contact, even though they originated from the same small region. As a result, inflation can produce a universe that is vastly larger than the region we can observe today. The observable universe becomes just one small bubble within a much larger space-time. This does not mean inflation automatically implies an infinite universe, but it does make an extremely large universe natural. Even a finite universe after inflation could be so large that its curvature and boundaries are effectively unobservable within our horizon. This helps explain why the observable universe appears so close to geometrically flat. In a small universe with noticeable curvature, parallel lines would converge or diverge noticeably over large distances. Observations show that on the largest scales we can measure, space appears very close to flat. Inflation provides a natural explanation for this. By stretching space so dramatically, any initial curvature is diluted. Just as the surface of a balloon looks flatter as it expands, a rapidly inflating universe looks flatter on local scales. This does not require the universe to be exactly flat or infinite. It only requires inflation to have lasted long enough to push curvature effects beyond our observable horizon. Another key effect of inflation is its impact on uniformity. Earlier sections noted that the early universe was remarkably uniform in temperature and density. Without inflation, this uniformity is difficult to explain because distant regions of the CMB sky should not have been in causal contact before recombination. Inflation changes that. Before inflation, the region that would later become our entire observable universe could have been small enough for all parts of it to interact and reach similar conditions. Inflation then stretched that uniform region to cosmic scales. In this way, inflation links causal contact in the early universe to large-scale uniformity observed much later. It does not remove the existence of horizons, but it reshapes their origin. Inflation also affects how we interpret the size of the universe relative to what we can see. If inflation occurred, then the observable universe is not representative of the whole in a simple way. It is a small sample of a much larger structure. This means that when we talk about the universe's size, we have to be careful. The size of the observable universe is well defined. The size of the entire universe is not directly measurable and may be vastly larger. Inflation also introduces a new way to think about the universe's beginning. In the simplest models, inflation occurs after the universe already exists in some form. It does not necessarily mark the absolute beginning of time or space. Instead, it marks a transition in how the universe expands. During inflation, the expansion is driven by a form of energy that behaves very differently from ordinary matter or radiation. This energy has the unusual property that its density remains nearly constant even as space expands. As space grows, more of this energy appears, driving further expansion. This feedback loop is what allows inflation to proceed so rapidly. Once inflation starts, it tends to continue until some mechanism causes it to end. When inflation ends, the energy driving it is converted into ordinary particles and radiation, reheating the universe and setting the stage for the hot plasma phase. From the standpoint of cosmic size, this reheating occurs after space has already been enormously stretched. The universe that emerges from inflation is already huge compared to its pre-inflation state. This has an important consequence for the idea of an edge. If inflation occurred, then the observable universe is not close to any physical boundary of the universe. Any edge or boundary that might exist would be far beyond our horizon, likely unreachable even in principle. Inflation therefore provides a natural explanation for why we do not see any signs of a boundary or edge in space. Not because none exists, but because inflation has pushed it far beyond observational reach. Another consequence of inflation is that it amplifies tiny quantum fluctuations. During inflation, microscopic fluctuations in fields are stretched to macroscopic scales. These fluctuations become the seeds of later structure formation. The density variations observed in the CMB originate from these amplified fluctuations. This means inflation not only affects the size of the universe, but also imprints a specific pattern on its structure. However, inflation does not make the universe uniform in every respect. It makes it uniform on large scales while still allowing small variations. This balance matches observations. The universe is smooth overall, but structured on smaller scales. In terms of size, inflation also complicates the question of whether the universe is finite or infinite. Some inflationary models produce a finite universe. Others produce a universe that is infinite in extent. Observations within our horizon cannot distinguish between these possibilities. This is not a weakness of observation. It is a consequence of inflation stretching space beyond any practical limit. Once regions are pushed beyond the event horizon, they cannot influence us or be observed, regardless of their size or structure. Inflation also affects how we think about what lies beyond the observable universe. Without inflation, one might imagine that regions just beyond our horizon are similar in scale and age to what we observe. With inflation, those regions may be unimaginably far away and may have undergone different local histories after inflation ended. This does not mean physical laws differ there, but it does mean that conditions could vary in ways we cannot test directly. Inflation increases the potential diversity of cosmic regions while simultaneously isolating them causally. Another important aspect of inflation is that it does not eliminate horizons. It reshapes them. Inflation creates a universe where horizons exist because of both early and late-time expansion. The particle horizon today reflects both the finite age of the universe and the effects of inflation in its earliest moments. In practical terms, inflation increases the distance between regions that were once causally connected. This means that when we look at the CMB, we are seeing regions that share a common inflationary origin but have been separated by enormous expansion. This separation is not just large, it is exponential. Small changes in the duration of inflation lead to enormous differences in the final size of the universe. As a result, even modest inflation can produce a universe far larger than the observable region. This sensitivity makes inflation particularly effective at explaining why the universe appears much larger than it needs to be to account for observations. Inflation also means that the universe's size cannot be inferred simply by extrapolating the current expansion backward in time. The expansion history includes a qualitatively different phase that dominates the size increase. Without inflation, the universe would still be large, but its size relative to the observable horizon would be much smaller. Inflation changes that ratio dramatically. Another subtle consequence is that inflation makes the universe's global properties largely inaccessible. Features such as overall topology or boundary conditions are effectively hidden beyond the horizon. The observable universe becomes a local patch with limited information about the whole. This does not make cosmology arbitrary. It means cosmology focuses on what can be inferred from within a finite region. Inflation sets the scale of that region relative to the whole. It is also worth emphasizing that inflation does not require the universe to expand into anything. As with later expansion, inflation is expansion of space itself. There is no external reference frame or surrounding space. From the perspective of an observer within the universe, inflation simply increases distances between points according to the evolving metric. There is no sense in which the universe occupies a larger region of some external space. Another point relevant to the universe's size is that inflation may not have happened everywhere in the same way or at the same time. Some models suggest that inflation could continue in some regions while ending in others. This can lead to a universe with vastly different regions, separated by enormous distances. However, regardless of the details, the key effect remains. Inflation dramatically increases the universe's size relative to what any single observer can see. This means that when discussing the universe's edge, inflation pushes that edge far beyond anything defined by current horizons. The observable universe becomes a small, causally connected island within a much larger expanse. Importantly, inflation does not remove the observational boundaries discussed earlier. The CMB remains the electromagnetic boundary. Event horizons still limit future influence. Inflation simply sets the initial conditions that determine how large the universe is relative to those boundaries. In that sense, inflation explains why the universe looks boundary-free within our observable region, while still allowing for the possibility that boundaries exist far beyond. The effect of inflation on size is therefore twofold. It makes the universe extremely large, and it makes its full extent inaccessible. Both outcomes follow naturally from rapid early expansion. This is why inflation plays such a central role in modern discussions of the universe's size. It does not just adjust details, it changes the scale of the entire cosmic picture. When cosmologists talk about the shape of the universe, they are not asking whether it looks like a sphere, a disk, or some other familiar object embedded in space. They are asking something more abstract and more fundamental: how space itself is shaped and how distances behave when extended over enormous scales. This question is about geometry, not appearance. On small scales, space behaves in ways that match everyday Euclidean intuition. Parallel lines stay parallel. The angles of a triangle add up to 180 degrees. Circles have circumferences equal to 2 pi times their radius, but these rules are not guaranteed to hold over very large distances. In general relativity, space can be curved, and that curvature affects how geometry works. There are 3 broad categories of spatial geometry relevant to cosmology: positive curvature, negative curvature, and zero curvature. These correspond roughly to closed, open, and flat universes. In a positively curved universe, space has a spherical geometry. Parallel lines eventually converge. The angles of a triangle add up to more than 180 degrees. If you travel far enough in a straight line, you could, in principle, return to your starting point. Such a universe would be finite in volume, though unbounded. There would be no edge you could fall off. In a negatively curved universe, space has a saddle-like geometry. Parallel lines diverge. The angles of a triangle add up to less than 180 degrees. Such a universe would be infinite in extent, with space continuing endlessly. In a flat universe, space has zero curvature. Parallel lines remain parallel. Triangles add up to exactly 180 degrees. This geometry matches the rules of Euclidean space, extended to cosmological scales. These geometries are not just mathematical possibilities. They have observable consequences. Curvature affects how light travels, how volumes grow with distance, and how large objects appear at different redshifts. This is why cosmologists can test the geometry of the universe using observations. One of the most powerful tools for this purpose is the cosmic microwave background. The CMB contains a characteristic pattern of temperature fluctuations with a known physical scale. By measuring how large these features appear on the sky, cosmologists can infer the geometry of space. If space is positively curved, those features appear larger than expected. If space is negatively curved, they appear smaller. If space is flat, they appear at the size predicted by Euclidean geometry. Measurements show that the universe is very close to flat. Within observational uncertainties, spatial curvature is consistent with zero. This result does not mean the universe is exactly flat in an absolute sense. It means that if curvature exists, it is so small that it cannot be detected within the observable universe. Any curvature radius would have to be far larger than the observable horizon. This has an important implication for the universe's size. If the universe is positively curved and finite, its total size must be much larger than the part we can see. If it were small, curvature effects would be obvious. The fact that we do not observe them means that either the universe is extremely large or it is infinite. Flatness, therefore, does not settle the question of finiteness versus infinity. A flat universe can be infinite. It can also be finite if it has a more complex topology, such as wrapping around on itself in subtle ways. Observations so far cannot distinguish between these possibilities. What flatness does tell us is that there is no nearby geometric edge. Space does not curve sharply or close in on itself anywhere within the observable region. There is no sign that traveling far enough in one direction would lead to a boundary or return point within accessible distances. This reinforces the idea that the observable universe is not near any global edge or boundary. Flatness also connects directly to the universe's expansion history. In the equations of cosmology, curvature competes with energy density. As the universe expands, the influence of curvature evolves differently from that of matter, radiation, and dark energy. Without a special mechanism, even tiny deviations from flatness in the early universe would grow over time, leading to a universe that is obviously curved today. The fact that we observe near flatness now implies that the early universe must have been extremely close to flat. This is known as the flatness problem, and it was one of the original motivations for inflation. Inflation naturally drives the universe toward flatness by rapidly expanding space and diluting any initial curvature. From a geometric perspective, inflation stretches space so much that any curvature becomes negligible within the observable patch. This does not require curvature to be exactly zero globally. It only requires inflation to have lasted long enough. This again emphasizes that geometry on the largest scales may be very different from what we can observe locally. Even if the universe has global curvature, inflation can hide it beyond our horizon. Another way to think about flatness is in terms of parallel transport. In curved space, moving a vector around a large loop can change its orientation. In flat space, it does not. Observations imply that over the largest loops we can test, space behaves as though it is flat. This is a statement about large-scale geometry, not about local gravitational effects. Local curvature caused by stars, galaxies, and clusters exists everywhere. But when averaged over immense distances, these local distortions cancel out, leaving an overall geometry that is nearly flat. This distinction matters because it separates local gravitational curvature from global spatial curvature. The presence of massive objects bending spacetime does not imply that the universe as a whole is curved in a global sense. Flatness also affects how volumes grow with distance. In a flat universe, the volume within a given radius grows as the cube of that radius. In curved universes, the growth is faster or slower. Observational consistency with flat volume growth provides another check on geometry. All of these tests converge on the same conclusion. Within the limits of what we can observe, space behaves as though it is flat. This does not mean the universe has no shape. It means that whatever its global shape is, it is hidden beyond our observational reach. Another important point is that flatness does not imply simplicity. A flat universe can have complex topology. Space could wrap around in multiple directions, connecting distant regions in ways that are not obvious locally. Such topologies would leave subtle patterns in the CMB, such as repeating structures. Searches for these patterns have not found convincing evidence so far. This suggests that if the universe has a finite but flat topology, its fundamental scale is larger than the observable universe. Again, the theme is repetition. The universe, if finite, is larger than what we can see. Flatness also influences how we interpret the universe's expansion. In a flat universe dominated by dark energy, expansion accelerates in a specific way that leads to the event horizons discussed earlier. Geometry and expansion are tightly linked. If the universe were strongly curved, the fate of expansion could be different. But near flatness combined with observed energy components leads to a universe where expansion continues and causal disconnection increases. This means geometry is not just an abstract property. It shapes the universe's long-term behavior and the accessibility of distant regions. Another subtle implication is that flatness makes the universe locally look infinite, even if it is not. Within our horizon, space extends smoothly in all directions, without noticeable curvature. This creates the intuitive sense that the universe goes on forever. Whether that intuition is correct globally remains unknown. Flatness allows both possibilities. What flatness definitively rules out is a small, tightly curved universe with a nearby geometric edge. Such a universe would leave obvious signatures that we do not observe. In summary, measurements of geometry show that space is very close to flat on the largest scales we can measure. This implies that the universe is either infinite or finite on scales far larger than the observable universe. In either case, geometry provides no evidence for a nearby edge. If an edge exists at all, it lies far beyond any horizon we can access. The question of whether the universe is finite or infinite sounds simple, but in cosmology it is one of the hardest questions to answer in a meaningful way. It is not hard because the math is unsolved or because observations are sloppy. It is hard because the universe only allows us to see a limited region, and that region may not be representative of the whole. To understand what finite and infinite mean in this context, we have to separate physical intuition from mathematical definitions. A finite universe is one that has a total volume that is limited. It contains a finite amount of space, even if that space has no edges. An infinite universe is one that extends without limit, containing an unbounded amount of space. Crucially, a finite universe does not require a boundary. This is one of the most common points of confusion. A classic analogy is the surface of a sphere. The surface area of a sphere is finite, but you can travel on it forever without encountering an edge. There is no point where the surface ends. Every location looks locally the same. This kind of geometry is finite but unbounded. Cosmological models allow for similar possibilities in 3 dimensions. Space can be finite without having a place where it stops or where physical laws break down. An infinite universe, by contrast, simply keeps going. No matter how far you travel, there is always more space beyond. There is no total volume, only endless extension. Both types of universes are allowed by general relativity. The equations themselves do not force one outcome over the other. The difference comes from the universe's global geometry and topology, not from local physics. From an observational standpoint, the difficulty is immediate. We can only observe a finite region of space. Even if the universe is infinite, we only ever see a finite patch of it. And if the universe is finite but very large, that finite patch may look indistinguishable from an infinite one. This means observations can rule out some possibilities, but they cannot settle the question completely. One way cosmologists approach the problem is by studying spatial curvature, as discussed earlier. Strong positive curvature would suggest a finite universe. Strong negative curvature would suggest an infinite one. Near zero curvature allows both. Measurements indicate that the universe is very close to flat. That alone does not answer the question. A flat universe can be infinite, but it can also be finite if space wraps around in a more complex way. This wrapping is known as topology. Topology describes how space is connected globally, independent of local curvature. For example, a flat 2-dimensional surface can be infinite like an endless plane, but it can also be finite like the surface of a torus which wraps around in 2 directions. Locally, both surfaces look flat. Only by exploring large distances could you tell the difference. The same idea applies in 3 dimensions. Space could be flat but finite if it wraps around itself in 1 or more directions. Traveling far enough in a straight line could eventually bring you back to your starting point without ever encountering an edge. If the universe has such a topology, its total size would be finite, but its geometry would still appear flat locally. The problem is that the scale of this wrapping, if it exists, must be larger than the observable universe. Otherwise, we would see repeating patterns in the distribution of galaxies or in the cosmic microwave background. Extensive searches have been conducted for such patterns. So far, none have been conclusively detected. This suggests that if the universe is finite with a wrapped topology, its fundamental size is larger than what we can observe. That pushes any global finiteness beyond direct confirmation. Another approach is to consider inflation. Inflation naturally produces a universe that looks flat and enormous, regardless of whether it is finite or infinite globally. Even if the universe is finite, inflation can make it so large that its curvature and boundaries are pushed far beyond our horizon. This means inflation weakens the observational distinction between finite and infinite models. Both become consistent with what we see. There is also a deeper issue. Infinity itself is not something physics handles casually. In mathematics, infinity is a well-defined concept. In physics, it often signals a limit of applicability. That does not mean the universe cannot be infinite, but it does mean that infinite quantities are treated with caution. An infinite universe would contain infinitely many galaxies, infinitely many stars, and infinitely many regions like our own observable universe. In such a universe, every physically allowed configuration of matter would occur infinitely many times. This has unsettling implications, but those implications alone do not rule out infinity. They simply highlight how different infinite systems are from finite ones. A finite universe avoids some of these conceptual issues, but it introduces others. If the universe is finite, what sets its size? Why that size and not another? Is it static, or does the total volume change over time? In expanding cosmologies, even a finite universe can increase its total volume. Expansion does not require infinity. A finite space can grow larger while remaining finite. So when cosmologists ask whether the universe is finite or infinite, they are not asking whether it is expanding. They are asking whether the expansion applies to a bounded or unbounded space. Another important distinction is between spatial infinity and temporal infinity. A universe can be infinite in space but finite in time, or finite in space but infinite in time. These are separate questions. The observable universe is finite in both space and time, but that tells us nothing definitive about the total universe. There is also the issue of observational equivalence. Two universes, one infinite and one finite but very large, can produce identical observations within a limited region. No experiment confined to that region can distinguish them. This means that, in principle, the question may be undecidable using observation alone. It may remain a question answered only by theoretical preference or by deeper physical principles not yet discovered. Some cosmologists argue that simplicity favors an infinite universe. Others argue that inflationary models naturally produce finite regions with complex global structure. There is no consensus. It is also worth noting that infinite does not mean everything imaginable exists. Physical laws still constrain what can exist. Infinity refers to extent, not arbitrariness. Likewise, finite does not mean small. A finite universe could be so large that its total size is effectively infinite for all practical purposes. From the standpoint of an observer, the difference may be irrelevant. If the universe is finite but larger than any horizon, it behaves observationally like an infinite one. This is why cosmology often focuses on the observable universe, rather than the total universe. The observable universe is what physics can directly constrain. However, the question of finiteness is not meaningless. It shapes how cosmologists think about initial conditions, global properties, and the interpretation of cosmological models. For example, in a finite universe, total energy may be easier to define. In an infinite universe, global quantities often diverge or become ambiguous. There are also implications for probability. In an infinite universe, any event with non-zero probability occurs infinitely many times. In a finite universe, probabilities behave more like they do in finite systems. These issues become especially relevant when discussing early universe physics, inflation, and possible multiverse scenarios, though those topics belong to later sections. For now, the key point is this: current observations do not tell us whether the universe is finite or infinite. They tell us that if the universe is finite, it is far larger than what we can see. And if it is infinite, we only ever experience a tiny part of it. There is no observational evidence for a physical edge, boundary, or termination of space within the observable universe. Geometry, expansion, and structure all behave as though space continues smoothly beyond our horizon. This does not prove infinity. It proves only that any finiteness lies beyond reach. The universe may be infinite, it may be finite, but unbounded. Both remain viable. What we can say with confidence is that the question cannot be answered by pointing a telescope in one direction and looking harder. It is a global question about the structure of space itself. and for now that structure extends beyond everything we can observe. The phrase, "the edge of the universe," suggests a picture that feels natural to human intuition. Space stretching outward until it reaches some kind of boundary, beyond which there is nothing. This picture shows up in questions about falling off the universe, hitting a wall, or reaching a place where space ends. In modern cosmology, this idea does not fit how space is understood. A physical edge would be a location where space itself stops existing. Beyond that point, there would be no distances, no directions, and no extension of physical laws. For such an edge to exist, space would have to be embedded in something else, with a boundary separating inside from outside. General relativity does not describe space this way. Space is not a substance placed inside a larger container. It is the set of relationships between events and distances defined by the metric of space-time. Asking where space ends is not like asking where land ends, an ocean begins. It is asking for a boundary in the structure that defines distance itself. This is why most cosmological models do not include physical edges. They include finite and infinite spaces, curved and flat geometries, but not borders where space abruptly stops. To see why, consider again the example of a finite but unbounded universe. In such a universe, space has a limited total volume, but every direction continues smoothly. There is no special location that marks an end. If you travel in any direction, the geometry continues consistently. There is no point where the equations of physics fail or where distances become undefined. A physical edge would require special conditions at that boundary. Physical laws would have to specify what happens there. Fields would need boundary conditions. Geodesics, paths of free-falling particles, would need rules for what happens when they reach the edge. No such boundary conditions appear naturally in cosmological models. This does not mean edges are logically impossible. It means they are not part of the frameworks that successfully describe observations. Another way to see the problem is to ask how an edge would behave under expansion. If the universe expands, does the edge move? If so, relative to what? Does it expand into something? These questions expose how poorly the idea fits with relativistic cosmology. In standard models, expansion is a property of space itself. Distances between points increase, but there is no external reference frame. There is nothing for space to expand into. An edge would reintroduce an external frame or surrounding space, which is not part of the theory. There is also the issue of observational signatures. If there were a physical edge within or near the observable universe, it would likely produce detectable effects. Light approaching an edge would behave strangely. Structures near the edge would have asymmetric gravitational environments. The distribution of matter and radiation would show anisotropies aligned with the boundary. We observe none of these effects. The universe looks statistically the same in all directions on large scales. This isotropy is one of the strongest empirical arguments against a nearby physical edge. Even if the edge were far away, beyond the observable universe, its existence would still raise conceptual problems. Why does the universe have that particular shape? Why does space end there and not elsewhere? What defines the boundary? Physics typically replaces such arbitrary features with dynamical explanations or deeper symmetries. The idea of an edge also conflicts with how cosmological horizons work. Horizons are limits on what can be observed or influenced, not limits on where space exists. The particle horizon marks how far light has traveled since the beginning of cosmic expansion. The event horizon marks how far light emitted now can ever travel. Neither is a physical barrier. Confusing horizons with edges is common, but they are fundamentally different. Horizons depend on time and expansion history. An edge would be a fixed feature of space itself. Another source of confusion comes from visualizing the universe from the outside. Diagrams often show the universe as a sphere growing in size, which can make it seem as though there is an outer surface. These diagrams are tools for visualization, not literal representations. The surface in such diagrams represents the set of all points at a given cosmic time, not a boundary in space. When drawn in higher dimensional embedding diagrams, it is easy to misinterpret the picture as implying an edge. In reality, the embedding space is not physical. In a closed universe, space is like the surface of a sphere, not the volume inside it. The surface has no edge, even though it is finite. In an open or flat universe, space extends indefinitely. Again, no edge, and there is also the issue of causality. If there were a physical edge, could signals reflect off it? Could information be lost or altered there? How would conservation laws behave? Modern cosmology does not require such complications to explain observations. Introducing a physical edge would create more problems than it solves. That said, some speculative theories consider boundaries in a broader sense. For example, in certain models of higher dimensional physics, our universe might be a lower dimensional surface, embedded in a higher dimensional space. In such models, what we perceive as the universe could have boundaries in the higher dimensional space. However, even in these scenarios, the effective three-dimensional space we experience typically has no edge. The boundary exists in a higher dimensional sense, not as a place you could travel to within space. Moreover, these ideas remain speculative and untested. They are not required to explain any current observation. From a practical standpoint, cosmologists avoid the concept of a physical edge because it lacks explanatory power and empirical support. Instead, they focus on well-defined, testable properties: geometry, expansion, curvature, topology, and horizons. And when people ask whether the universe has an edge, the most accurate answer is not simply no. It is that the question assumes a structure that space does not appear to have. Space, as described by modern physics, does not end the way objects in space do. If the universe is finite, it is finite without an edge. If it is infinite, it has no edge by definition. In neither case is there a place where you could reach the end of space. This does not mean the universe is fully understood. It means that the intuitive picture of a cosmic boundary is not compatible with how space behaves in the theories that match observations. The idea of an edge is a powerful metaphor, but it is a misleading one. What we do have are observational limits and causal horizons. These feel like edges because they limit access. But they are not features of space itself. They are features of our position in time and the universe's expansion history. So when asking whether the universe has a physical edge, the answer given by modern cosmology is consistent and clear. There is no evidence for one and no need for one in our best models. One of the most persistent sources of confusion in cosmology is the difference between a horizon and a boundary. The two ideas feel similar because both limit what we can access. But physically, they are completely different. A boundary is a place where something ends. A horizon is a limit on what can be seen, reached, or influenced, given the universe's history and expansion. In everyday experience, boundaries are common. A wall stops motion. A shoreline marks the end of land. These are physical features embedded in space. Horizons, by contrast, are usually perceptual or causal. They arise from constraints on information flow, not from the termination of the medium itself. Cosmological horizons fall into the second category. They are not places in space where anything stops existing. They are consequences of finite signal speed and cosmic expansion. The most familiar example is the horizon on Earth. Standing on a flat plane, the ground does not suddenly end at the horizon. The horizon exists because the Earth curves away from your line of sight. It limits what you can see, not what exists. Cosmological horizons work in an analogous way, but the cause is not curvature of the ground. It is the expansion of space combined with the finite speed of light. There are two main horizons relevant to cosmology: the particle horizon and the event horizon. The particle horizon marks the maximum distance from which light has had time to reach us since the beginning of cosmic expansion. Because the universe has a finite age, light from regions beyond this distance has not yet arrived. This creates a boundary in observation, not in space. Those regions exist. They simply lie beyond our observational reach at the present time. The size of the particle horizon grows as time passes. As the universe ages, light from more distant regions has time to reach us. The observable universe expands. A boundary, by contrast, would not move outward as time passes. It would be a fixed feature of space itself. The event horizon is a different concept. It marks the maximum distance from which light emitted now will ever be able to reach us in the future. In universes with accelerated expansion, there are regions that are currently visible but will never be able to influence us again after a certain time. This creates a future limit on causal contact. It does not remove the existence of those regions. It simply isolates them. Unlike the particle horizon, the event horizon does not necessarily grow indefinitely. In an accelerating universe like ours, it approaches a finite size. Again, this is not a wall. Light emitted beyond the event horizon is not stopped by anything. It simply never makes progress toward us fast enough to overcome the expansion of space. Horizons also depend on the observer. Different observers at different locations or times have different horizons. A boundary, by contrast, would be observer-independent. This observer dependence is one of the clearest indicators that horizons are not physical edges. Another important distinction is that horizons are dynamic. Their locations change over time as the universe expands and as expansion rates evolve. Boundaries, if they exist, would require special physical rules. Horizons require no new physics. They emerge naturally from relativity and the finite speed of light. Horizons also do not reflect or absorb light in a physical sense. There is no interaction at the horizon. Light crossing a horizon does not notice anything special locally. From the perspective of the photon, nothing happens at the horizon. The horizon exists only in the global description of space-time. This again contrasts with a boundary, where local physics would necessarily change. The cosmic microwave background is sometimes mistakenly described as a boundary. In reality, it is closer to a horizon, but even that is not quite right. The CMB marks the time when the universe became transparent to light. It is a temporal boundary in our observations, not a spatial boundary in the universe. The surface of last scattering is not a shell you could travel to. It is a set of events distributed throughout space at a particular time in cosmic history. Every observer sees their own surface of last scattering centered on themselves. This alone shows it cannot be a physical boundary. Horizons also do not imply symmetry breaking or special directions. The universe looks statistically the same in all directions because horizons are centered on the observer, not fixed in space. If there were a physical boundary, the universe would look different in the direction of that boundary. We observe no such directional dependence. Another way to see the distinction is through causal diagrams. In space-time diagrams, horizons appear as light-like surfaces, separating regions that can exchange signals from those that cannot. Boundaries would appear as edges of the space-time manifold itself. The standard cosmological space-time has horizons but no edges. It is also important to emphasize that horizons are not absolute. What lies beyond them can change with time. Regions beyond today's particle horizon may become observable in the future if expansion conditions allow. Similarly, regions beyond the event horizon today were once observable in the past. This fluidity makes horizons fundamentally different from edges. Confusing horizons with boundaries leads to misunderstandings about the universe's structure. It leads people to imagine a cosmic shell or wall, when in reality, the limitation is about information, not existence. The universe does not end at our horizon. Our access to it does. This distinction matters because it shapes how cosmologists interpret observational limits. When we say something is unobservable, we are not saying it is absent. We are saying it is causally disconnected from us at the moment. Boundaries, if they existed, would require new physics to explain why space ends there. Horizons require only the physics we already have. This is why modern cosmology treats horizons as central concepts and boundaries as unnecessary. Understanding this difference dissolves many apparent paradoxes about edges, centers, and the size of the universe. The universe can be finite without boundaries, it can be infinite without edges, and it can have horizons without walls. Those statements sound contradictory only if horizons and boundaries are treated as the same thing. They are not. When cosmologists talk about the observable universe, they are not referring to a special region with physical walls or a distinct composition. They are describing a region defined entirely by causal limits. The observable universe is best thought of as a bubble centered on the observer, not because it is physically special, but because observation itself is local. This bubble is defined by the particle horizon. It includes all regions of space from which light has had time to reach the observer since cosmic expansion began. Everything outside this region exists just as much as what is inside, but it has not had time to influence the observer. The bubble metaphor is useful because it emphasizes symmetry. Every observer, no matter where they are located, has their own observable universe centered on themselves. There is no preferred center of the cosmos. If you were located in a distant galaxy, Your observable universe would include regions that are currently beyond our horizon, and it would exclude some regions we can currently see. This alone shows that the observable universe is not a physical structure. It is a perspectival one. The radius of this bubble is set by the finite age of the universe and the expansion history of space. It is not equal to the age of the universe multiplied by the speed of light, because space has been expanding while light travels. As a result, the radius of the observable universe today is much larger than the naive distance light would travel in the universe's age if space were static. This bubble has a boundary in observation, but not in substance. There is no shell of matter or energy marking its edge. The boundary is simply the set of points whose light is just now reaching the observer. The cosmic microwave background lies very close to this observational boundary. It represents the oldest light we can see. However, as discussed earlier, it is not a spatial wall. It is a time slice. Every direction you look, the CMB comes from a different region of space, but all from nearly the same cosmic time. This gives the illusion of a spherical surface surrounding us, but that surface exists only in our past light cone. The bubble also grows with time. As the universe ages, light from more distant regions reaches us. The particle horizon expands, and the observable universe increases in size. This growth does not mean that the universe itself is expanding faster or changing its global structure. It means our observational reach is increasing. At the same time, the event horizon can limit future access. Some regions currently inside the observable universe may eventually cross the event horizon and become forever causally disconnected. This leads to a subtle but important point. The observable universe at any given time is not the same as the set of regions that will ever be observable. The bubble is dynamic, shaped by the interplay between expansion history and cosmic acceleration. Another feature of the bubble is that it contains a representative sample of the universe, but not necessarily a complete one. If the universe is homogeneous on large scales, then any sufficiently large region looks statistically similar to any other. Observations suggest that this is the case. On large scales, matter and energy are distributed uniformly, with only small fluctuations. This homogeneity allows cosmologists to treat the observable universe as a fair sample of the whole, even though it is only a small part. However, inflation complicates this picture. Inflation allows for the possibility that regions beyond our observable universe could have different large-scale properties, even if local physics is the same. This does not mean physical laws differ there. It means initial conditions could vary in ways that are unobservable to us. In this sense, the bubble may not be fully representative of the entire universe. It is representative of our causal patch. This idea becomes especially important when discussing questions of probability and typicality in cosmology. What is typical within the observable universe may not be typical globally. The bubble metaphor also clarifies why we cannot observe an edge. If the universe has a boundary or a global structure beyond our horizon, it is not accessible from within our bubble. This is not because of a lack of technology, but because of the structure of space-time itself. No matter how powerful our telescopes become, they cannot collect light that has not yet reached us, or that will never reach us. The observable universe is therefore not an engineering limitation. It is a fundamental one. Another aspect of the bubble is that it is centered on the observer at the current time. If you consider observations at different times, the shape and content of the observable universe change. Looking back in time always means looking at smaller, denser versions of the universe. The bubble contains different epochs layered by distance. This layering is why cosmological observation is also a form of time travel. Distant objects are seen as they were, not as they are now. The bubble contains this entire temporal archive bounded by the CMB. The idea of the observable universe as a bubble also helps explain why cosmology relies so heavily on statistical methods. We cannot compare multiple independent bubbles. We only have access to one. This makes cosmology different from laboratory science, where experiments can be repeated under controlled conditions. Instead, cosmologists test theories by checking whether a single observable universe is consistent with predictions derived from physical laws. This limitation does not make cosmology unscientific. It makes it a science constrained by global uniqueness. Finally, the bubble perspective removes the temptation to imagine a physical boundary just beyond our reach. There is nothing special at the edge of the observable universe. Crossing that edge, if it were possible, would not feel like crossing anything. It would simply extend your observational reach in a different frame. The bubble exists because of our position in space-time, not because the universe has walls. Understanding the observable universe this way reframes many questions about edges, centers, and limits. It shifts the focus from where space ends to how information flows. And that shift is essential for making sense of what the universe allows us to see and what it keeps beyond reach. Once the observable universe is understood as a causal bubble rather than a physical container, the natural next question becomes unavoidable. What lies beyond it? The difficulty is that this question cannot be answered in the same way as questions about stars or galaxies. Beyond the observable universe, there is no direct data. Everything we say is constrained inference. The simplest and most conservative assumption is that regions beyond our horizon are broadly similar to the regions within it. This assumption is not arbitrary. It is grounded in the observed large-scale uniformity of the universe and in the success of physical laws that apply everywhere we can test them. If the universe is homogeneous and isotropic on sufficiently large scales, then any large enough region should statistically resemble any other. Under this assumption, what lies beyond our horizon is more of the same: galaxies, dark matter, dark energy, and the same physical laws. This does not mean exact repetition. Local structures would differ, but the overall statistical properties would match. However, inflation introduces the possibility that this assumption may only be approximately true. Inflation can stretch small regions to enormous sizes, but it can also amplify quantum fluctuations and freeze them into large-scale features. In some inflationary models, these processes can lead to different regions having slightly different properties after inflation ends. These differences might include variations in density, the amplitude of fluctuations, or other large-scale parameters. Importantly, this does not imply different laws of physics. The underlying equations remain the same. What varies are initial conditions. From within our observable universe, there is no way to directly test whether such variations exist beyond our horizon. All we can do is look for indirect signatures, such as unusual patterns or anomalies, near the largest observable scales. So far, observations are consistent with large-scale uniformity, but they do not rule out variation beyond the horizon. Another possibility is that the universe is finite but extremely large. In that case, beyond the observable universe there is still more space, but eventually, if one could travel far enough, one might return to the starting point due to the universe's topology. If this were true, the region beyond our horizon could include copies of structures similar to those we see, but arranged in a way that reflects the global topology. Again, the scale required for this would have to be larger than the observable universe, or we would already see repeating patterns. Another possibility is that the universe is infinite. In an infinite universe, what lies beyond our horizon is simply more universe, without end. In such a case, there would be infinitely many regions like our observable universe, separated by distances we can never cross. This leads to philosophical implications, but physically it is a straightforward extension of uniformity. More speculative ideas suggest that what lies beyond our horizon could be very different in character. Some models of eternal inflation propose that inflation continues in some regions while ending in others, producing a vast collection of regions with different histories. In these models, our observable universe would be one region among many, each causally disconnected from the others. Within such a framework, regions beyond our horizon might not share the same large-scale properties, even if local physics is similar. However, these ideas remain speculative. They are motivated by theoretical considerations, not by direct evidence. What can be said with confidence is limited. Beyond the observable universe, space continues. There is no indication that it stops or behaves differently in a way that would affect us. The horizon does not mark a change in physical laws. It marks a limit in causal connection. It is also important to note that beyond does not mean outside in a spatial sense. The observable universe does not sit inside a larger container with a surrounding region. Beyond the horizon simply means regions whose light has not reached us. If you were located beyond our horizon, you would see your own observable universe, centered on you, which would include regions currently beyond our reach and exclude some we can see. This symmetry reinforces the idea that nothing special happens at the horizon. Another constraint comes from consistency. Whatever lies beyond must be compatible with what we observe within. For example, large-scale anisotropies or sharp boundaries beyond the horizon would tend to produce observable effects within our region over time. The absence of such effects suggests continuity rather than abrupt change. However, this argument has limits. Some changes could exist beyond the horizon without producing observable signatures. The key point is that our ignorance is not total, but it is fundamental. We can say that beyond the observable universe there is more space-time governed by the same physical laws we know. We cannot say how large it is, whether it is finite or infinite, or whether its global properties match our local patch exactly. This uncertainty is not a failure of cosmology. It is a reflection of causal structure. Physics is built on what can be tested. Regions forever outside causal contact cannot be tested, no matter how advanced technology becomes. This does not make speculation useless, but it places it in a different category. Cosmologists use theoretical models to explore what could lie beyond the horizon, but they distinguish clearly between what is supported by observation and what is extrapolation. This distinction is essential for avoiding confusion between evidence and imagination. When people ask what lies beyond the observable universe, they often imagine exotic realms or dramatic transitions. The most likely answer, based on current knowledge, is far more mundane, more universe. Not empty space, not a wall, not a different reality. Just regions of space-time we cannot see. That answer may feel unsatisfying, but it is consistent with everything we know about how space, time, and causality work. Until new physics provides testable ways to probe beyond horizons, that is as far as the question can be taken. And that limitation is built into the structure of the universe itself, not into our instruments or our imagination. One of the most persistent misunderstandings about the universe's expansion is the idea that galaxies are moving through space away from some central point, heading toward an edge. This picture feels intuitive because it matches everyday experiences of explosions and outward motion. But it does not describe what cosmological expansion actually is. In modern cosmology, expansion refers to the growth of distances between points in space, not to objects traveling through space away from a center. This distinction is subtle but essential. Galaxies are not flying outward into empty space. On large scales, they are mostly at rest relative to the expanding fabric of space itself. The increase in distance between them happens because the metric that defines distance is changing with time. This is why cosmology does not assign a center to the expansion. Every observer sees distant galaxies moving away from them, regardless of location. This symmetry would be impossible if expansion were ordinary motion through space. If the universe were expanding from a central point into pre-existing space, observers near that center would see something very different from observers near the edge. We observe no such difference. The expansion of space is encoded mathematically in the scale factor, a function that tells us how distances between co-moving points change over time. Co-moving points are locations that move with the expansion, remaining at fixed coordinates as space stretches. Galaxies that are not gravitationally bound to each other are approximately co-moving. Their increasing separation reflects the increase of the scale factor, not propulsion or force. This is why the expansion does not produce drag, heating, or resistance. Objects are not pushing through anything. The balloon analogy is often used to explain this. Points on the surface of an inflating balloon move farther apart as the balloon expands, even though none of the points are moving across the surface. The surface itself is stretching. The analogy has limits, but it captures the key idea. Expansion is intrinsic to space, not motion within it. Because expansion is not motion, it does not obey the usual speed limits in the same way. At sufficiently large distances, the rate at which space expands between 2 points can exceed the speed of light. This does not violate relativity because no object is locally moving faster than light. This fact often causes confusion. When cosmologists say distant galaxies recede faster than light, they are describing the growth of space between us and them, not superluminal travel through space. This distinction matters for understanding edges. If galaxies were flying through space, one might imagine them eventually reaching the edge of the universe. But if expansion is the stretching of space itself, there is no destination they are heading toward. There is no outside region being filled. Space is not expanding into anything. This also clarifies why asking, "What is the universe expanding into?" is a misplaced question. Expansion does not require an external container. The universe's geometry and expansion are defined internally by relationships between events and distances. There is no background space relative to which expansion occurs. Another implication is that expansion affects everything uniformly on large scales. There is no preferred direction of expansion. Space stretches the same way everywhere. This uniformity explains why the universe looks isotropic. If expansion were directional or centered, we would see anisotropies aligned with that structure. Local structures resist expansion. Gravity binds galaxies, solar systems, planets, and atoms. Expansion becomes noticeable only on scales where gravity is weak enough that space's stretching dominates. This is why galaxies do not expand internally, even though the universe as a whole is expanding. This also shows that expansion is not a force. There is no outward push trying to tear objects apart. It is simply the evolution of the space-time metric. Another important point is that expansion can coexist with finite or infinite space. A finite universe can expand without developing an edge. An infinite universe can expand while remaining infinite. Expansion changes distances, not topology. This directly undermines the intuition that expansion must create or reveal an edge. Stretching a surface does not produce a boundary if one did not already exist. If the universe had no edge before expansion, expansion does not generate one. Conversely, if the universe were finite but unbounded, expansion would increase its total volume while preserving the absence of edges. Understanding expansion as metric growth also clarifies the meaning of recession velocity. Recession velocity is not a velocity through space. It is a rate of increase of distance due to expansion. This is why recession velocity depends on distance. The farther away a galaxy is, the more space there is between us and it, and the more that space can stretch. This relationship is captured by Hubble's law. It is not a statement about motion away from a center. It is a statement about how expansion affects separation. Because expansion is global, it does not single out any location as special. Every observer can consider themselves at rest while seeing the same large-scale behavior. This symmetry is incompatible with the idea of an edge reached by expansion. Another common misconception is that expansion is slowing galaxies down or carrying them away like debris in a blast. In reality, galaxies can have peculiar velocities, motions through space relative to the expansion, on top of the general expansion. These peculiar velocities can point in any direction and can even overcome expansion locally. This shows again that expansion is not a motion imposed on objects. It is a background change in how distances are defined. When cosmologists run simulations of the universe, they do not place galaxies in empty space and push them outward. They define an expanding metric and let matter evolve within it. This framework has been extraordinarily successful in explaining observations, from galaxy distributions to the cosmic microwave background. Within this framework, there is simply no role for an edge created by expansion. Expansion also affects time. The rate of expansion changes over cosmic history, influenced by radiation, matter, and dark energy. This history shapes horizons and observational limits, but it does not introduce boundaries in space. Understanding expansion correctly dissolves many apparent paradoxes about the universe's size and structure. It explains why there is no center, no edge, and no outside. The universe expands everywhere at once in the only way expansion can occur, when space itself is what is changing. The discovery that the universe's expansion is accelerating added a new layer to the question of cosmic limits. Expansion alone already creates horizons. Accelerated expansion reshapes them in a more permanent way. This acceleration is attributed to dark energy, a component of the universe that dominates its large-scale behavior. Dark energy is not a force pushing galaxies outward. Like expansion itself, it is best understood as a property of space-time. It affects how the expansion rate evolves over time. Observations show that, in the current era, dark energy makes up most of the universe's total energy density. Its defining feature is that its density does not dilute significantly as space expands. As the universe grows larger, dark energy becomes increasingly dominant. This dominance changes the long-term causal structure of the universe. In a universe without dark energy or with only matter and radiation, expansion slows over time. Horizons grow, and regions that are currently out of contact may eventually become observable. With dark energy, the opposite happens on the larger scales. Expansion accelerates, and some regions that are currently observable will eventually become permanently inaccessible. This is where the event horizon becomes central. The event horizon marks the maximum distance from which light emitted now, or in the future, can ever reach us. In an accelerating universe, this horizon approaches a fixed size. Regions beyond that distance are not blocked by anything. They simply recede in such a way that light they emit never gains ground against the expansion of space. Over time, more and more of the universe crosses this horizon. Galaxies that are not gravitationally bound to us will eventually pass beyond the event horizon. Once they do, no signal they send after that moment will ever reach us. This process is gradual and relentless. There is no sudden disappearance, no dramatic cutoff. Distant galaxies fade, redshift, and eventually become undetectable. Importantly, nothing physical happens to those galaxies at the horizon. They do not hit a wall or cross a boundary in their own frame. Locally, their physics proceeds exactly as before. The isolation is mutual but asymmetric in experience. We lose causal contact with them, and they lose causal contact with us. This means the observable universe in the far future will be much smaller than it is today, not in physical size but in accessible content. Over extremely long timescales, only the local group of galaxies, which is gravitationally bound, will remain visible. Everything else will have crossed beyond the event horizon. This future isolation is sometimes described as the universe becoming emptier, but that description can be misleading. The universe does not lose matter or energy globally. It loses connectivity. Dark energy creates a universe that fragments into causally isolated regions, each evolving independently. This fragmentation does not imply edges between regions. It implies expanding separation. Each region still exists within the same space-time. They are just unable to influence one another. This has profound implications for what the universe will look like to observers in the far future. From their perspective, the observable universe will contain only their local gravitationally bound structures. The cosmic microwave background will be redshifted beyond detectability. Evidence of expansion itself may become inaccessible. This does not mean the expansion stops. It means the observational clues fade beyond reach. Dark energy therefore creates a kind of observational end state, not a boundary in space, but a limit in information. This also reframes the idea of an edge. Instead of asking where space ends, dark energy forces us to ask where causal influence ends. The answer depends on time. Today, our event horizon encloses a vast region. In the far future, that region will effectively shrink in terms of observable structure. Yet even then, there is no physical edge. Space continues smoothly beyond the horizon, just as it does today. Another subtle implication is that dark energy makes the universe's global structure increasingly irrelevant to any one observer. As causal isolation increases, local conditions dominate experience. Questions about the total size of the universe become even less testable over time. This reinforces a recurring theme. Cosmology is shaped not just by what exists, but by what can ever be observed. Dark energy imposes a permanent limit on that observability. It is also important to distinguish between isolation and emptiness. The regions beyond our horizon are not empty. They contain galaxies, radiation, and structure just like ours, at least in the simplest models. They are empty only in the sense that they no longer exchange information with us. This distinction matters because it avoids turning horizons into edges. Horizons isolate, they do not terminate. Dark energy does not carve the universe into separate spaces. It stretches space in a way that weakens connections over time. From a global perspective, the universe remains a single space-time. From a local perspective, it becomes increasingly solitary. This duality is central to understanding why accelerated expansion feels like it creates boundaries, even though it does not. The ultimate effect of dark energy is not to reveal an edge, but to hide more and more of the universe from any given observer. In that sense, dark energy makes the universe effectively smaller in terms of accessible information while making it larger in terms of physical extent. Both happen simultaneously. This combination, endless expansion and increasing isolation, is one of the most counterintuitive outcomes of modern cosmology. but it follows directly from treating expansion as a property of space and dark energy as a persistent component of that space. There is no final wall. There is no last frontier. There is only a horizon that slowly closes in terms of influence, not existence. Even after understanding expansion, horizons, geometry, and causal limits, the idea of an edge keeps returning. This persistence is not a failure of explanation. It reflects how human intuition is shaped by experiences that do not scale to cosmology. Human intuition is built in environments that are finite, bounded, and embedded in larger contexts. Rooms have walls. Landscapes end at oceans or cliffs. Objects exist inside containers. Motion usually means movement through a surrounding medium. These experiences quietly train the mind to expect boundaries. When we apply these expectations to the universe, we unconsciously assume that space itself must behave like the objects inside it. If something has size, we expect it to have an outside. If something expands, we expect it to expand into something else. Cosmology violates both expectations. Space is not an object in space. It is the structure that defines what distance even means. Asking for the edge of space is like asking for the edge of distance itself. The language sounds sensible, but the concept does not map cleanly onto physical theory. Another source of confusion is scale. On human scales, every expansion we encounter involves motion through space. Explosions, inflating objects, spreading fluids, all of them expand within a pre-existing environment. There is no everyday analogue for metric expansion, where distances grow without motion through a background. Even the balloon analogy, useful as it is, can reinforce the wrong intuition. People naturally imagine the balloon expanding into the surrounding air, and then transfer that image to the universe. But the surrounding air in the analogy has no physical counterpart. It is a visual crutch, not a feature of reality. Maps also mislead intuition. When we draw the universe as a sphere or circle, the boundary of the drawing looks like an edge. The drawing inevitably places the universe inside a larger empty space on the page. The mind then treats that empty space as something real. In reality, the embedding space in such diagrams is mathematical, not physical. It exists to help visualize curvature, not to represent an external region. Another reason the idea of an edge feels natural is that horizons behave like edges in practical terms. They limit access. They prevent interaction. They define what can and cannot be reached. Functionally, this feels like an edge, even though it is not one. When people hear that we cannot see beyond a certain distance, the brain fills in the picture with a wall or boundary. It is hard to accept a limit that is not a thing. Language also contributes to the problem. Words like boundary, surface, and edge are used metaphorically in cosmology. The surface of last scattering sounds like a shell, even though it is a time-defined set of events. Once a metaphor takes hold, it becomes difficult to separate it from literal meaning. Another intuitive trap comes from imagining the universe from the outside. People ask what the universe looks like as a whole, as if there were a vantage point beyond it. But there is no external viewpoint in cosmology. All observations are internal. The universe does not present itself as an object that can be stepped back from. This absence of an outside perspective is deeply counterintuitive. The mind wants a camera angle that physics does not provide. There is also a psychological component. An edge provides closure. It offers a satisfying answer to the question, where does it end? An endless structure without boundaries feels incomplete or unsettling. Infinity and unboundedness resist mental compression. In this sense, the idea of an edge is emotionally comforting. It turns the universe into something with a manageable shape. Science often advances by abandoning comforting intuitions. The loss of a central Earth, the loss of absolute time, and the loss of a static universe all required letting go of deeply held mental models. The loss of a cosmic edge belongs to the same category. Another reason the edge idea survives is that it sometimes appears to be supported by incomplete explanations. When expansion is described without care, it sounds like galaxies are moving away from a center. When the observable universe is described without emphasis on observer dependence, it sounds like a special region surrounded by emptiness. Each simplification plants a seed of misunderstanding. This is not a failure of education so much as a mismatch between language evolved for survival and concepts required for cosmology. Even professional physicists rely on mathematical structures that bypass intuition entirely. The equations do not contain edges because they do not require them. The geometry, expansion, and dynamics all work without specifying where space ends. Another subtle source of confusion is the idea of finiteness. Finite objects usually have edges. Finite volumes in everyday life are enclosed. But finiteness in geometry does not require enclosure. A finite space can be self-contained. This distinction rarely appears in ordinary experience, so the mind substitutes the closest familiar concept: a boundary. The idea of time also plays a role. People sometimes imagine the universe as starting at a point and growing outward, like a ripple expanding in water. This again imposes a center and an edge where none exist. In cosmology, the beginning of expansion happens everywhere at once. There is no location where it started earlier or later. This everywhere at once beginning is one of the hardest ideas to internalize. The persistence of the edge intuition, then, is not a sign that the concept is secretly correct. It is a sign that the universe violates expectations built from small-scale experience. Understanding this helps explain why the question keeps resurfacing, even after detailed explanations. It also explains why different people ask the same question in slightly different ways, each time hoping to reveal a hidden boundary. They are not missing information. They are colliding with the limits of intuition. Recognizing this is useful because it reframes the problem. The challenge is not to find the edge. The challenge is to unlearn the expectation that one must exist. Cosmology does not deny edges arbitrarily. It simply describes a universe in which they are unnecessary. Once that is accepted, many related confusions dissolve. The universe does not need an outside. It does not need a container. It does not need a final wall. Those needs belong to the human mind, not to space-time. By this point, the pattern should be clear. Every time the idea of an edge seems to appear, it turns out to be something else. A horizon mistaken for a boundary. A limit on information mistaken for a limit on existence. A feature of observation mistaken for a feature of space itself. This is not accidental. The word edge survives because it is trying to do too much work. In everyday life, an edge is where something ends. In cosmology, nothing we observe behaves that way. Space does not terminate. Physical laws do not abruptly stop. There is no location where the universe runs out. What does exist are limits, hard limits, but they are limits of access, not limits of reality. The most important of these is causality. The universe has a finite age. Light travels at a finite speed. Space expands. Those three facts alone guarantee that no observer can ever see the whole universe, even if the universe itself is finite. That limitation creates horizons. Horizons feel like edges because they separate the knowable from the unknowable. But they are not physical structures. They are bookkeeping boundaries defined by time, speed, and expansion history. Once that distinction is made, the idea of an edge changes meaning. There is no spatial edge you could approach. There is no boundary you could collide with. There is no outer surface where physics breaks. Instead, there are three kinds of limits that get conflated into the word edge. First, observational limits. We cannot see beyond the particle horizon because light from those regions has not reached us. This limit depends on time. It moves. It is different for every observer. Second, causal limits. Because expansion is accelerating, some regions will never influence us, no matter how long we wait. This creates permanent isolation, not termination. Third, conceptual limits. Questions about the universe's total size, topology, or global structure may never be empirically answerable. Not because the universe is hiding something, but because causality forbids access. None of these are edges in the traditional sense. When cosmology says there is no edge, it is not saying the universe is simple or fully understood or intuitively satisfying. It is saying that the structure we observe does not require, predict, or accommodate a physical endpoint of space. If the universe is infinite, there is no edge by definition. If the universe is finite, it is finite in the same way a curved surface is finite, self-contained, unbounded, and without a place where space stops. If inflation occurred, any global boundaries are pushed so far beyond our horizon that they are observationally irrelevant. If dark energy continues to dominate, more of the universe will become causally inaccessible over time, but nothing will vanish or end. Every route leads to the same conclusion. The universe has limits without having an edge. This reframes the original question in a more accurate way. The meaningful question is not, where is the edge of the universe? The meaningful questions are, what can we observe? What can ever influence us? What can be inferred, even indirectly? And what lies forever beyond testability? Modern cosmology answers those questions with remarkable precision. It tells us how horizons form, how they evolve, and how they constrain knowledge. It tells us why the universe looks smooth, flat, and boundary-free on the larger scales we can measure. What it does not do is satisfy the intuition that everything must end somewhere. That intuition evolved in a world of cliffs, shelters, and finite territories. It was never designed to handle space-time. Once that is accepted, the absence of an edge stops being frustrating and starts being informative. It tells us something profound about reality. The universe is not an object inside a larger arena. It is the arena, and arenas do not have edges in the way objects do. What feels like an unanswered question is actually a category error. The universe does not refuse to show us its edge, it simply does not have one to show. And the deeper lesson is this: the limits we encounter in cosmology are not where reality ends. They are where our position within reality stops giving us access. That distinction between existence and accessibility is the real boundary modern cosmology reveals. Nothing beyond it needs to be imagined as a wall. The universe is not unfinished. It is just bigger than any single viewpoint can contain. After all the clarifications, distinctions, and dismantling of false intuitions, it can be tempting to conclude that the question of the universe's edge is simply misguided and therefore unimportant. That would be a mistake. The question matters precisely because it exposes how deep cosmology really goes and where its limits genuinely lie. Asking about an edge is not a naive error. It is a probe. It tests whether the universe is something that can be fully mapped, bounded, and conceptually contained, or whether it resists that kind of closure. Historically, questions like this have driven major advances. Asking where the sky ends led to heliocentrism. Asking whether time is absolute led to relativity. Asking whether the universe has an edge forces us to confront the difference between physical reality and observational access. This question matters because it separates three ideas that are easy to blur together: existence, observation, and explanation. Something can exist without being observable. Something can be observable without being fully explainable. And something can be explainable without ever being directly tested. The edge of the universe sits exactly at that intersection. From a scientific standpoint, the absence of an edge is not a gap, it is a prediction. Our best theories describe space-time in a way that does not require termination points. The fact that observations align with that description is non-trivial. If space had a nearby boundary, cosmology would look very different. Expansion would behave differently. Large-scale symmetry would be broken. Observations would point toward preferred directions or asymmetries. They do not. That consistency gives confidence that the framework is not missing an obvious structural feature. At the same time, the question matters because it highlights the limits of what science can promise. Cosmology is often mistaken for a field that claims total knowledge. In reality, it is one of the clearest demonstrations of epistemic humility in science. Cosmology openly admits that some aspects of the universe may be forever inaccessible. Not unknown for now. Not unknown because of technical limitations. Unknown because of causal structure. That is a profound statement about reality. The edge question also matters because it shapes how we interpret more speculative ideas. Concepts like multiverses, eternal inflation, or varying initial conditions only make sense once it is clear that beyond the observable universe is not the same as beyond the universe. Without that clarity, speculation turns into confusion. With it, speculation can at least be properly framed. There is also a practical reason the question matters. Many misconceptions about cosmology originate from misunderstandings about edges, centers, and expansion. Clearing this up improves public understanding of everything from the Big Bang to dark energy. When people imagine the universe expanding into emptiness, they misinterpret redshift. When they imagine a central point, they misinterpret isotropy. When they imagine a boundary, they misinterpret horizons. These errors propagate. The edge question is therefore a diagnostic tool. If it is answered carefully, many other concepts fall into place. On a deeper level, the question matters because it confronts a basic human expectation that reality should be fully surveyable from the outside. Physics has been steadily dismantling that expectation for over a century. There is no privileged frame of reference, no universal clock, no external vantage point. The absence of an edge fits that pattern. It tells us that the universe is not something we stand outside of and examine. It is something we are embedded within. That has philosophical implications, but it is not philosophy imposed on physics. It is physics pointing toward a conclusion that philosophy must reckon with. And another reason the question remains important is that it keeps cosmology honest. It prevents premature claims about the shape of everything or the total size of reality. By forcing cosmologists to distinguish between what is measured and what is inferred, the edge question guards against overreach. It also keeps open the possibility of surprise. While current evidence points strongly away from physical edges, cosmology remains empirical. If future observations uncovered unexpected large-scale anisotropies or violations of homogeneity, the conversation would change. The fact that such discoveries are even conceivable shows that the question is not meaningless. It is constrained but not forbidden. Finally, the question matters because it is one of the few that naturally leads people from intuition to formal reasoning. It invites curiosity, then demands precision. You cannot answer it with metaphor alone. You cannot answer it with equations alone. You have to bridge the two. That bridge is where real understanding forms. So when people ask where the universe ends, the correct response is not to dismiss the question, but to translate it. They are really asking, what are the ultimate limits of observation? What does space-time allow or forbid? And how much of reality can any one observer ever access? Those are not trivial questions. They are among the deepest questions science can ask. The answer is not a wall, it is a structure where reality extends beyond visibility, where space does not require an outside, and where limits arise from time, light, and expansion, rather than from boundaries. That is why the edge question persists. And that is why, even once answered, it continues to matter. Once synthesis is allowed, the question of the universe's edge stops being about cosmology alone. It becomes a mirror. Not because the universe is anthropocentric, but because the limits we keep encountering are tied directly to how observation, knowledge, and position work in any physical reality. What the universe reveals over and over is that there is a sharp distinction between what exists and what can be accessed. That distinction is not negotiable. It is built into space-time itself. For most of human history, those two ideas were assumed to be the same. If something existed, it was assumed that, in principle, one could go there, see it, or reach it. The edge question inherits that assumption. If the universe exists as a whole, surely there must be some way to point to its limits. Modern cosmology breaks that assumption cleanly. The universe does not hide its edge, it demonstrates that existence does not require accessibility. This is not an abstract philosophical position layered onto physics. It is a direct consequence of three empirical facts. The universe has a finite age, light has a finite speed, and space evolves over time. From those alone, limits emerge naturally. Nothing about that is arbitrary. Once that framework is accepted, the universe stops looking incomplete and starts looking internally consistent. The lack of an edge is not a missing piece. It is a feature of how space-time works. This has an important implication. The universe is not constructed to be fully surveyed. There is no cosmic vantage point from which everything lines up neatly. There is no final map that includes all regions equally. Every observer is embedded, local, and constrained. That is not a defect of observers. It is a property of reality. In that sense, the universe treats all observers the same way. No one gets privileged access. No one sees the whole thing. Every viewpoint is partial by necessity. This symmetry is one of the most quietly radical aspects of modern cosmology. It means that asking for the universe's edge is similar to asking for the universe's external reference frame. The question assumes a structure that the universe does not provide. Once that assumption is dropped, the frustration dissolves. What remains is something subtler and more powerful. A universe that is coherent without being fully containable by any single perspective. This realization also reframes humanity's place in the cosmos. not as central, not as marginal, but as situated. We exist at a particular location, at a particular time, with a particular horizon of access. That horizon is not an accident. It is the same kind of horizon any observer would have anywhere. From another galaxy billions of light years away, observers would draw their own observable universe. It would overlap with ours in some regions and diverge in others. Neither would be more real. There is no master version. This alone undermines the instinct to search for a final edge. If every observer has their own horizon, which one would count as the boundary? The idea collapses under its own weight. The edge question also teaches a deeper lesson about scientific explanations. The most satisfying explanations are not always the ones that give closure. They are the ones that eliminate unnecessary assumptions. An edge sounds like closure, but it adds structure without evidence. Removing it simplifies the universe, even if that simplicity is counterintuitive. That is a recurring theme in physics. Absolute time was simpler than relativity. A fixed Earth was simpler than orbital mechanics. A static universe was simpler than expansion. Each time, intuition resisted. Each time, reality won. The absence of an edge belongs in that lineage. It also reshapes how we think about future discovery. There is a temptation to believe that with better instruments, larger telescopes, or more advanced probes, we will eventually see it all. Cosmology is clear that this is not how it works. Some limits are technological. Those can be pushed. Some limits are physical. Those cannot. No matter how advanced a civilization becomes, no matter how long it exists, no observer can step outside space-time to inspect it from the outside. No observer can outrun cosmic horizons. No observer can access regions that are causally disconnected. This is not pessimism, it is precision. And it has a surprising upside. It makes what is accessible more meaningful. The observable universe is not a small sample of a much larger, more important reality. It is the only reality that can ever matter to us in a causal sense. Everything we can test, verify, or be influenced by lives within that domain. That does not diminish what lies beyond. It simply places it in the correct category, real but unreachable. Once that distinction is clear, cosmology becomes less about chasing unreachable boundaries and more about understanding the structure we are actually embedded in. The edge question then turns out to be a gateway question. It leads people from naive realism to relational realism, from thinking of the universe as an object to understanding it as a network of relations defined by space-time. That shift is subtle, but it changes everything. It changes how we interpret beginnings. It changes how we interpret size. It changes how we interpret isolation. And it changes how we interpret our own limitations. The universe is not withholding answers. It is enforcing consistency. There is no final curtain to pull back, no hidden rim waiting to be revealed. There is only an expanding space-time with rules that apply everywhere, including to knowledge itself. In that sense, the edge of the universe does exist, but not where people expect. It exists at the boundary between what can, in principle, be known and what cannot. That boundary is not fixed, it is not spatial, it is not something you travel toward, it is something you are always already inside of, and once that is understood, the original question no longer feels unanswered. It feels resolved not by adding a missing piece, but by removing a mistaken one. The universe does not end. Our access does. Subscribe